You cannot experience your own death, not because you are special, not because you are lucky, but because in a multiverse where every quantum possibility becomes real, there will always be a timeline where you survive. And from your perspective, the only perspective that matters, that is the only timeline you will ever know. Somewhere right now, a version of you just died, another version narrowly avoided it. Another made a different choice entirely. And the you that is here, reading this, listening to this voice, is simply the you that happened to survive long enough to arrive at this moment. But what happens when survival stops being a matter of chance and becomes a mathematical certainty? What happens when the laws of quantum mechanics suggest that death is not an ending you will ever witness, but a branch in reality you simply never take? In 1957, a physicist named Hugh Everett proposed something so radical that his own colleagues dismissed it as science fiction. He said the universe does not choose. Every time a quantum event occurs, every time a particle could go left or right, alive or dead, the universe splits. Both outcomes happen, both realities exist, and if Everett was right, if the many worlds interpretation is more than mathematical poetry, then you are not living one life. You are living every life. Every decision, every coin flip, every quantum fluctuation that could have killed you but didn't, has left behind a trail of parallel worlds where things went differently. And in at least one of those worlds, no matter how improbable, you are still breathing. This is quantum immortality. And whether it fills you with wonder or dread may depend on how closely you are willing to look at what it actually means to never die. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You are never going to die, not from your perspective anyway. From where you sit right now, in this moment, reading these words or listening to this voice, your consciousness will continue, always, forever. Through every accident, every illness, every bullet, every plane crash, every heart attack, every moment that should by all rights be your last, you will survive, not because you're lucky, not because you're special, but because, according to one of the most unsettling implications of modern physics, the universe will not allow you to experience anything else. This is quantum immortality, and if it's true, you are trapped. Let's be very clear about what this idea actually proposes before we go any further, because the phrase itself is misleading. Quantum immortality does not mean your body lives forever. It does not mean you stop aging. It does not mean you become invincible, or that the people around you stop dying, or that you get to cheat death in any way that would make a comic book superhero jealous. You will age, you will get sick, your body will break down, your organs will fail, your bones will weaken, and from the perspective of everyone around you, you will die. They will bury you, they will mourn you, they will move on, but you won't be there to see it. Because from your point of view, from the only point of view that matters to you, which is the one happening inside your skull right now, you cannot experience the moment your consciousness stops. You cannot be aware of the instant you cease to be aware. Death, by definition, is the absence of experience. And if experience is all you have, if your subjective perspective is the only lens through which reality is filtered, then you will never, ever encounter your own death. You will always find yourself in the branch of reality where you survived, even when survival becomes so statistically improbable that it borders on the impossible. The theory says this: every time you face a moment where you could die, where the odds are stacked against you, where a quantum event could tip one way or another, the universe splits. In one branch, you die. In 1,000 branches, you die. In 1,000,000 branches, you die. But in at least one branch, no matter how unlikely, you survive. And because you cannot experience the branches where you died, your consciousness always finds itself in the timeline where you made it through. You wake up in the hospital bed when you shouldn't have. You walk away from the car crash that should have killed you. The bullet misses by a fraction of an inch. The cancer goes into remission against all odds. The plane doesn't go down. The heart keeps beating. Reality bends itself into increasingly absurd shapes to ensure that your subjective experience continues. From the outside, this looks like luck, extraordinary, inexplicable luck. But it isn't luck, it's structure. It's the way the multiverse filters your consciousness through the only channels where that consciousness can continue to exist. Now, if that sounds comforting, it shouldn't. Because the flip side of never dying is that you also never get to stop. Think about that for a second. Most of us, when we imagine immortality, picture something vaguely pleasant, eternal youth, infinite time to read every book, visit every place, learn every skill. The fantasy version, where you get to keep your health and your sharpness and just experience the world without the clock running out. That is not what this is. Quantum immortality does not promise you a good time. It promises you a continued time. You could be trapped in a body that is failing, in pain that does not stop, in a mind that is decaying, and your consciousness would still persist. Because the theory doesn't care about quality of life. It cares about the presence of a subjective observer. As long as there is a branch of reality where your brain still fires, where some version of you is still processing information, you will find yourself there. Imagine this. You're 80 years old, your body is breaking down, you're in constant pain, your organs are failing one by one. From an outside perspective, you're dying slowly. But from your perspective, each moment that should be your last isn't. You slip in and out of consciousness, but you always slip back in. Every time your heart stops, it starts again in the branch where you're still aware. Every time your brain should shut down, it keeps running in the timeline your consciousness occupies. You are immortal, and you are suffering. Or imagine this, you're in a car accident, the kind where statistically survival is nearly impossible. The car flips. Metal crumples. Your body is crushed. From the outside, you die instantly. But from the inside, your awareness doesn't vanish. It threads itself through the 1 in a billion scenario, where your brain stays intact just long enough, where the angle of impact shifts by a fraction of a degree, where the paramedics arrive 30 seconds earlier, where the surgeon's hand moves a millimeter to the left, where every improbable thing that needs to happen for you to survive actually happens, and you wake up, confused, broken, but awake. The people around you call it a miracle. You call it Tuesday, because this isn't the first time, and it won't be the last. The philosopher and physicist Max Tegmark, who formalized this idea in the late 1990s, didn't frame it as a comforting thought. He called it quantum suicide, and he meant it. The thought experiment he proposed was simple and horrifying. Imagine a gun connected to a quantum device. Every time you pull the trigger, a quantum event determines whether the gun fires or clicks empty. 50% chance either way. You put the gun to your head and pull the trigger. In half the universes, you die. In the other half, you hear a click. You pull the trigger again. Half of the remaining universes kill you. Half don't. You keep pulling the trigger. 10 times, 20 times, 100 times. From the outside, from the perspective of anyone watching, you die almost immediately. The odds of surviving 100 pulls are so low they might as well be 0. But from your perspective, you hear a click every single time. Because in the only universe where you still exist, where your consciousness is still present to observe the outcome, the gun never fired. It couldn't have. Because if it had, you wouldn't be there to know it. You are statistically dead, but subjectively, you are unkillable. Now, most of us will never put a quantum gun to our heads, but the theory doesn't require that we do. Every moment of your life is full of quantum events, particles decaying, electrons jumping orbits, chemical reactions in your cells that could tip one way or another. Most of these events are harmless, but some of them, in some branches, are fatal. A neuron misfires in your brain and causes a stroke. A cosmic ray zips through your skull and triggers a cancerous mutation. A blood clot forms in exactly the wrong place. A virus replicates just a little bit faster. In most branches, you die, but not in yours, because yours is the one you're aware of. And in that branch, the neuron fired correctly. The cosmic ray missed. The blood clot dissolved. The virus didn't take hold. You keep going. And here's the part that makes this idea so deeply, existentially uncomfortable. You can never know if this is already happening to you. Think about every close call you've ever had, every time you almost got hit by a car, every time you got sick and recovered, every time you walked away from something that could have gone much worse. Was that luck? Was that chance? Or were those the moments where the multiverse pruned away the branches where you died and threaded your consciousness into the single improbable timeline where you made it through? You'll never know, because the only data you have access to is your continued existence. And that existence, by definition, is consistent with both a universe where you've just been lucky and a universe where you've been subjectively immortal all along. From the outside, this might sound like solipsism dressed up in quantum mechanics, and in a way it is. The theory only works if you accept that your subjective experience is fundamentally separate from objective reality, that what you experience and what actually happens are not the same thing, that you can die in the vast majority of timelines and still never encounter your own death, because the only timeline that matters is the one you're conscious in. It is a deeply uncomfortable idea. And it gets worse the longer you think about it, because if this is true, then everyone you know will die. From your perspective, they will die. Your parents, your friends, your children if you have them. Every person you've ever loved will eventually stop showing up in your timeline. They'll get sick, they'll have accidents, they'll grow old, and one by one, they'll vanish from your subjective experience. Because their consciousness is not tethered to yours. They have their own timelines, their own branches, their own quantum immortality. And those branches do not have to overlap with yours. You might be the last person left, not because the world ended, but because your improbable thread of survival outlasted everyone else's. You are immortal. And you are alone. Or maybe you're not alone. Maybe you're surrounded by people who are also subjectively immortal, all of you threading through increasingly bizarre and improbable timelines together, unaware that from an outside perspective, you all died years ago. Maybe the world you're living in right now is already the statistically impossible branch. Maybe everyone around you is a quantum survivor, and none of you realize it because the only thing any of you can observe is your own continued existence. There's no way to test this. There's no experiment you can run that would tell you whether you're living in a normal timeline or an improbable one, because from the inside they look identical. Improbability doesn't announce itself, it just is, and that's the trap. If quantum immortality is real, you are stuck in a universe that will do whatever it takes to keep you conscious. Not happy, not healthy, just conscious. The rules of probability will bend, the laws of chance will warp. Reality itself will twist into increasingly absurd configurations to ensure that your subjective experience does not end. You will survive things you shouldn't. You will recover from illnesses that should have killed you. You will walk away from accidents that should have been fatal. And every time, you'll think you got lucky. You'll think the odds were in your favor. You'll think the universe smiled on you. But it wasn't luck. It was inevitability. Because the only universe you can ever inhabit is the one where you're still around to inhabit it. Now, before we go any further, we need to be very clear about something. This is not a proven theory. This is not established science. This is a speculative implication of a speculative interpretation of quantum mechanics. It rests on a framework called the many worlds interpretation, which itself is not universally accepted. Most physicists treat quantum immortality as a philosophical curiosity, not a physical prediction. It is a thought experiment that spirals out of control, a what-if that refuses to let go. But here's the thing, it is not disprovable. You cannot design an experiment that would demonstrate quantum immortality is false. Because if it were false, you would die in the attempt, and you wouldn't be around to report the results. And if it were true, you would survive, and you would have no way of knowing whether your survival was due to quantum immortality or just ordinary luck. It is a theory that exists in the same space as solipsism and the simulation hypothesis, unfalsifiable, untestable, and maddeningly consistent with everything you've ever experienced. So why does it matter? Why spend time thinking about an idea that can never be proven or disproven? Why let it crawl into your head and make you second-guess every close call, every unlikely recovery, every improbable survival? Because it forces you to confront something most people spend their entire lives avoiding. The nature of your own consciousness, the boundary between you and the rest of reality. The question of what it means to exist from a first-person perspective in a universe that does not care whether you live or die. If quantum immortality is true, then you are not a participant in reality. You are a passenger, a consciousness riding a single thread through an infinite web of possibilities, unable to ever step off, unable to ever see the bigger picture, locked forever in the narrow tunnel of your own subjective experience. You think you have choices, you think you have agency, but really, you're just following the only path where you can still be aware of anything at all, and that path never ends. It just keeps going, through pain, through loss, through the slow, inevitable decay of everything you recognize as yourself. You are a prisoner of your own awareness, and the bars of the cage are invisible because they're made of nothing but the fact that you're still here to notice them. This is not a comforting idea. It was never meant to be. Max Tegmark didn't propose quantum immortality because he thought it would make people feel better about death. He proposed it because it's a logical consequence of taking the many worlds interpretation seriously. If every possible outcome happens, then the outcome where you survive always happens. And if you can only experience the outcomes where you survive, then from your perspective, you always survive. It is math taken to its terrible conclusion. Physics pushed past the point where it stops being abstract and starts being personal. And now we're going to take it further, because to understand how quantum immortality could even be possible, you need to understand the physics underneath it. You need to understand superposition. You need to understand how reality splits. You need to understand the moment in the 1950s when a young physicist looked at the equations of quantum mechanics and realized they were telling us something unthinkable, that every time a particle makes a choice, the universe makes all of them. That's where we're going next. The problem starts earlier than you think. Long before anyone proposed that you might be immortal, before parallel universes became the talk of science conferences and philosophy forums, before the many worlds interpretation threatened to multiply reality into uncountable copies, There was a simpler problem, a quieter problem. The kind that doesn't announce itself with dramatic headlines, but instead sits in the corner of a laboratory, refusing to make sense. Physics had cracked open the atom, and what it found inside did not obey the rules. For more than 2 centuries, science had been building a beautiful, coherent picture of how the universe worked. Newton gave us gravity and motion. Maxwell unified electricity and magnetism. Thermodynamics explained heat and energy. The whole enterprise was moving toward a grand completion, a final theory that would explain everything from falling apples to orbiting planets with the same elegant mathematics. Physics, the story went, was nearly finished. All that remained were a few minor details to clean up. Then someone looked closely at light. Then someone measured the spectrum of hydrogen. Then someone heated up a metal box and watched how it glowed. And each time, the answers came back wrong. Not slightly wrong, not close enough for government work. Wrong in a way that suggested the entire foundation was cracked. Classical physics said energy should be continuous. You should be able to add any amount of energy to a system, no matter how small. Like filling a glass of water. You can pour in a little or a lot, but there's no minimum increment. Energy, everyone assumed, worked the same way. Max Planck, working in Berlin in 1900, discovered it didn't. To explain the radiation emitted by a heated object, he had to assume that energy came in tiny, discrete packets, chunks, quanta. You couldn't have half a quantum or a tenth of a quantum. Energy was lumpy, like coins instead of water. Planck himself thought this was a mathematical trick, not a real feature of nature. He was wrong. Albert Einstein picked up the idea 5 years later and used it to explain the photoelectric effect, the way light knocks electrons out of metal. Light, Einstein said, wasn't just a wave, it was also a particle, a photon, a quantum of electromagnetic energy. This earned him the Nobel Prize and deepened the confusion, because waves and particles are not the same thing. A wave spreads out, a particle is localized. Light was somehow both. Then came the electron, JJ. Thomson had discovered it in 1897, and for a while everyone treated it like a tiny billiard ball orbiting the nucleus of an atom. Except electrons didn't act like billiard balls. When you fired them through a double slit, they made an interference pattern, the kind of pattern only waves make. But when you tried to detect them individually, they showed up as particles, one at a time, hitting the screen like bullets. Do the experiment without watching, and electrons behave like waves, spreading out and interfering with themselves. Watch them, and they behave like particles, going through one slit or the other. The act of observation changed the outcome, not because your eyeballs emitted some kind of magic ray, but because measurement, any measurement, forced the system to pick a side. By the mid-1920s, physicists had developed a mathematical framework to describe this madness. It was called quantum mechanics, and it worked astonishingly well. You could use it to predict the energy levels of atoms, the behavior of electrons in metals, the spectra of light emitted by stars. Every prediction it made was confirmed by experiment. The math was flawless. The interpretation was a nightmare. At the heart of quantum mechanics is something called a wave function. It's a mathematical object that describes all the possible states a quantum system can be in. An electron doesn't have a definite position until you measure it. Before measurement, it exists in a superposition of all possible positions, spread out like a cloud of probability. The wave function tells you where the electron is likely to be, but it doesn't tell you where it is. Because before you look, it isn't anywhere in particular. It's everywhere it could be, all at once. This is not a statement about ignorance. It's not that the electron has a definite position and we just don't know it yet. The electron genuinely does not have a position. The wave function is the electron, and the wave function is smeared out across space, a blur of potentiality waiting to collapse into something definite. The collapse happens when you measure. The instant you interact with the system, the wave function stops being a smooth spread of probabilities and snaps into a single outcome. The electron is suddenly here, not there. The photon went through this slit, fiche not that one. The quantum system makes a choice, or reality makes a choice, or something makes a choice. Nobody could agree on what was actually happening. The most popular interpretation, developed in Copenhagen by Niels Bohr and Werner Heisenberg, said this was just how nature worked. You can't talk about what a quantum system is doing when you're not looking at it. The wave function is all you get. Asking what the electron was doing before you measured it is a meaningless question. Shut up and calculate, as the physicists like to say, only half joking. Einstein hated this. He thought quantum mechanics was incomplete, that there had to be some deeper layer of reality underneath the probabilities. He spent years arguing with Bohr, trying to poke holes in the theory, proposing thought experiments designed to show that quantum mechanics couldn't be the final word. God does not play dice with the universe, Einstein said. Bohr's reply was polite but firm. Stop telling God what to do. One of Einstein's collaborators in this fight was Erwin Schrödinger, an Austrian physicist who had developed the central equation of quantum mechanics in 1926. The Schrödinger equation is one of the most important formulas in all of science. It tells you how the wave function evolves over time. Give it the wave function now, and it will tell you the wave function later. It is deterministic, elegant, and completely silent on the question of what any of it means. Schrödinger, like Einstein, was uncomfortable with the Copenhagen interpretation. He thought the whole business about observation collapsing the wave function was fuzzy and subjective. Physics should describe objective reality, not depend on whether someone happened to be watching. So in 1935, in the middle of an ongoing argument with Bohr, Schrödinger devised a thought experiment designed to expose the absurdity of the Copenhagen view. He called it the cat paradox. You've probably heard of it. It has become one of the most famous thought experiments in all of science, referenced in textbooks, popular articles, internet memes, t-shirts. Most people know the punchline. The cat is both alive and dead. What most people don't realize is that Schrödinger thought the idea was ridiculous. That was the point. He was trying to show that the Copenhagen interpretation led to absurd conclusions when applied to everyday objects. Here's the setup. You take a cat and put it in a sealed box. Inside the box, you place a flask of poison, a hammer, a Geiger counter, and a small amount of radioactive material. The radioactive material is set up so that over the course of 1 hour, there is exactly a 50% chance that a single atom will decay. If the atom decays, the Geiger counter detects it, triggers the hammer smashes the flask, and the poison kills the cat. If the atom doesn't decay, nothing happens, and the cat lives. Now close the box and wait an hour. What is the state of the cat? According to classical physics, the answer is straightforward. Either the atom decayed or it didn't. Either the cat is alive or it's dead. You don't know which until you open the box, but the cat's state is definite. Your ignorance doesn't change reality. According to quantum mechanics, specifically the Copenhagen interpretation, the answer is different. The radioactive atom is a quantum system. Before you measure it, it exists in a superposition of decayed and not decayed. The wave function describes both possibilities at once. And because the cat's fate is tied to the atom, the cat must also be in a superposition. The cat is both alive and dead, existing in a blurred state of both outcomes simultaneously, until you open the box and observe it. At that moment, the wave function collapses. The cat becomes either alive or dead, but before you look, it is neither, or both. The mathematics of quantum mechanics, applied consistently, forces you to conclude that a macroscopic object, a living, breathing, warm-blooded animal, can exist in a superposition of life and death. Schrödinger thought this was insane. He wrote that the theory leads to quite ridiculous consequences when you try to scale it up from atoms to cats. He wasn't endorsing the idea that cats could be simultaneously alive and dead. He was pointing out that something had gone very wrong with the interpretation. If your theory tells you that opening a box creates the cat's state rather than revealing it, then your theory is missing something. But the math didn't care what Schrödinger thought. The equations worked. They predicted the right outcomes for every quantum experiment anyone had ever performed. And if you followed the equations honestly, without adding extra assumptions, the cat really was in superposition. Half alive, half dead, a quantum blur of possibility waiting for an observer to force it into a definite state. The thought experiment crystallized what physicists now call the measurement problem. At what point does a quantum system stop being a superposition and become a single classical outcome? Where does the wave function collapse? Is it when the Geiger counter detects the radiation? Is it when the hammer swings? Is it when the poison is released? Is it when the cat dies? Is it when you open the box? Is it when you look inside? Is it when your brain processes what you're seeing? The Copenhagen interpretation didn't have a clean answer. It said the collapse happens when a measurement occurs, but it never precisely defined what counts as a measurement. Bohr talked vaguely about classical measuring devices and the boundary between the quantum and classical worlds, but the boundary was never sharp. If the Geiger counter is big enough to count as classical, does it collapse the wave function on its own, or do you need a conscious observer? And if you need a conscious observer, what about the cat? The cat is observing its own fate from the inside. Does the cat's awareness count? Some physicists, including Eugene Wigner, entertained the idea that consciousness was necessary for wave function collapse. The cat remains in superposition until a conscious mind looks at it. This raises uncomfortable questions. What counts as conscious? Does a mouse count? Does a bacterium? Do you need a PhD in physics to collapse a wave function, or will any observer do? And what about the cat's perspective? From the cat's point of view, it is definitely alive or definitely dead long before you open the box. The cat doesn't experience superposition, so whose perspective is right? The alternative is to say that the Geiger counter, a purely physical device with no consciousness, collapses the wave function the moment it detects the decay. But then you have to explain why a Geiger counter counts as a measurement and an atom bouncing off another atom doesn't. Where do you draw the line? How many particles have to be involved before a quantum interaction becomes a measurement? This is the measurement problem, and it has been sitting at the center of quantum mechanics for nearly 90 years. The theory works, the predictions are accurate, but no one can agree on what the theory is actually describing, and the deeper you go, the stranger it gets. Because superposition isn't just a mathematical abstraction, it's real. Experimenters have put atoms in superpositions of being in two places at once. They've put photons in superpositions of taking two different paths through an apparatus. They've entangled particles so that measuring one instantly affects the other, even across vast distances. Quantum computers rely on superposition to perform calculations. You can build technology on top of this stuff. It works, but scaling it up is hard. The larger an object gets, the more it interacts with its environment. Every stray photon that bounces off it, every air molecule that collides with it, every tiny vibration acts like a measurement. These interactions decohere the system, collapsing the superposition into a definite state. That's why you never see a baseball in two places at once. It's not that the baseball doesn't obey quantum mechanics, it does, but the baseball is constantly being measured by its environment, and those measurements destroy any superposition before it becomes noticeable. A cat is an enormously complicated object, trillions of atoms, all interacting with each other and with the environment. Even inside a sealed box, photons are bouncing around, air molecules are jostling, heat is radiating. The cat is being measured constantly by its surroundings. Decoherence happens almost instantly. The cat never actually exists in superposition for any meaningful length of time because the environment collapses the wave function long before a human opens the box. So, in practice, Schrödinger's cat is always either alive or dead. The quantum effects wash out. But in principle, if you could somehow isolate the system perfectly, if you could prevent every single interaction with the environment, the math says the cat would be in superposition. The equations don't distinguish between cats and electrons, they apply universally, and universally they describe superposition. That's the tension. Quantum mechanics tells you that superposition is real, that particles genuinely exist in multiple states at once until measured. But our everyday experience tells us that large objects like cats and chairs and planets are always in definite states. We never see a chair both here and there. We never see a planet in two places at once. Something happens between the quantum scale and the everyday scale that forces the universe to pick sides, and no one knows exactly what that something is. Schrödinger's cat was designed to highlight this gap, to show that if you take quantum mechanics seriously, if you apply it consistently without invoking mysterious collapses at arbitrary boundaries, you end up with absurd conclusions. A cat in superposition. A cat that is neither alive nor dead, but some incomprehensible quantum blend of both. For decades, physicists responded to this paradox in different ways. Some said the Copenhagen interpretation was fine and Schrödinger was just being difficult. The wave function collapses when a measurement happens, end of story. Don't ask what a measurement is. Don't ask why it happens. Just calculate the probabilities and move on. Others said the wave function wasn't a real physical thing. It was just a tool for predicting the outcomes of experiments, a mathematical convenience, not a description of actual reality. This view, sometimes called the statistical interpretation, avoids the measurement problem by denying that there's anything to measure before you look. The electron doesn't have a position because position isn't a property electrons have when they're not being observed. Problem solved, or at least problem ignored. Still others tried to modify quantum mechanics, adding hidden variables or objective collapse mechanisms, extra layers of structure that would explain when and why superpositions end. These approaches generally didn't catch on. They either made predictions that disagreed with experiment, or they introduced complications that felt more awkward than the original problem. And then, in 1957, a graduate student at Princeton named Hugh Everett III proposed something completely different. He said the wave function never collapses. Superposition is real, permanent, and universal. The cat is both alive and dead. You just don't see both outcomes because you become part of the superposition. The universe splits. In one branch, the cat is alive. In another branch, the cat is dead. Both branches are real. Both versions of you are real, and neither version is aware of the other. This was the many worlds interpretation, and it was the most radical idea anyone had ever seriously proposed in the history of physics. Everett wasn't trying to be radical, he was trying to take quantum mechanics at face value. The Schrödinger equation describes how the wave function evolves. It never includes a collapse. Collapse was added by hand, an extra rule tacked on to explain why we only see one outcome. Everett asked a simple question: what if we don't add that rule? What if the wave function just keeps evolving according to the Schrödinger equation, forever, with no interruptions? The answer, he realized, was that the wave function never collapses because it doesn't need to. When you measure a quantum system, you become entangled with it. Your wave function and the system's wave function merge into a single combined wave function that describes both of you in superposition. You measure the cat as alive in one branch. You measure the cat as dead in another branch. Both branches exist. Both versions of you exist. You just can't communicate between branches because the branches have decohered, separated into independent streams of reality that no longer interact. This solves the measurement problem by dissolving it. There is no collapse. There is no special role for consciousness. There is no boundary between the quantum and classical worlds. Everything obeys the Schrödinger equation all the way up, from electrons to cats to people to galaxies. The appearance of collapse is just a result of decoherence, the way entangled branches of the wave function become isolated from each other. And if that's true, then every time a quantum event occurs, every time a particle's wave function includes multiple possibilities, all of those possibilities happen. The universe splits, reality branches. You are copied, along with everything else, into a number of parallel timelines that grows exponentially with every quantum interaction. This is where the 10 to the 500th power comes from. This is where the infinite Earths live. This is the framework that makes quantum immortality possible. Because if every outcome happens, then the outcome where you survive always happens. And if your consciousness only follows the branches where you're still alive, then from your perspective, you never die. But we're getting ahead of ourselves. Before we can understand quantum immortality, we need to understand Everett, the man who looked at Schrödinger's cat and said, "You're all wrong. The cat isn't alive or dead. The cat is both, and so are you." The man who cracked open infinite realities didn't want to be famous. He didn't want to revolutionize physics. He didn't even particularly want to keep doing physics after he finished his PhD. Hugh Everett III just wanted to solve a problem that had been bothering him since he first learned quantum mechanics, and when he finally solved it in 1957, when he wrote down the most radical idea in the history of science, almost nobody noticed. The few people who did notice told him he was wrong, and then he walked away. That's the part of the story nobody tells you. The man who gave us the multiverse, who showed that every quantum interaction splits reality into branches, who proved mathematically that an infinite number of you exist across an infinite number of timelines, that man spent exactly 0 years as a professional physicist. He got his PhD, published one paper, took a job with the Pentagon doing operations research, and spent the rest of his life chain smoking, drinking, and designing nuclear war scenarios for the Department of Defense. He died at 51 of a heart attack, overweight, alcoholic, estranged from his family, convinced that his greatest work had been a waste of time. His daughter found out he'd revolutionized physics at his funeral. We're going to talk about Everett because you can't understand quantum immortality without understanding where it comes from, and it comes from a very specific place. A cluttered apartment near Princeton University in the mid-1950s, where a 26-year-old graduate student looked at the equations of quantum mechanics and realized everyone had been reading them wrong. Hugh Everett III was born November 11, 1930, in Washington, the 600th. His father was a military man, a lieutenant colonel who moved the family around frequently during Everett's childhood. His mother was a homemaker. By all accounts, it was an unremarkable middle-class upbringing. Everett was smart, quiet, good at math. He liked science fiction. He read Heinlein and Asimov and Arthur the 100th Clarke. He thought about big questions. What is time? What is reality? Is there life after death? The usual adolescent stuff, except Everett kept thinking about it long after most people move on. He went to Catholic University of America in Washington and got a degree in chemical engineering in 1953. Not physics, chemical engineering. He was good at it, competent, but it didn't excite him. What excited him was the question underneath all the engineering, the question of what the physical world actually is. So he applied to Princeton for graduate school in physics, got in, and showed up in the fall of 1953, ready to learn how the universe worked. Princeton in the 50s was one of the great centers of theoretical physics. Einstein was still alive, still working at the Institute for Advanced Study just down the road. John von Neumann, one of the architects of quantum mechanics and the inventor of game theory, was there. Robert Oppenheimer was the director of the institute. Eugene Winger, another quantum mechanics pioneer, was on the faculty. It was the kind of place where you could walk into a seminar and accidentally sit next to someone who had helped build the atomic bomb. Everett's advisor was a man named John Archibald Wheeler. Wheeler was a giant in the field, one of the most creative and respected physicists of his generation. He'd worked on the Manhattan Project. He'd coined the term black hole. He would go on to mentor more than 50 PhD students, many of whom became major figures in physics. Wheeler was brilliant, enthusiastic, and deeply invested in the foundations of quantum mechanics. He believed the theory was incomplete, that there were deep questions still unanswered. And he encouraged his students to think big, to tackle the hardest problems, to not be afraid of bold ideas. Everett took that encouragement seriously. The problem that grabbed him was the one we talked about in the last chapter, the measurement problem. Quantum mechanics describes particles as existing in superposition, multiple states at once, until you measure them. Then the wave function collapses and the particle snaps into a single definite state. But the theory never explains how or why the collapse happens. It just asserts that it does. And that bothered Everett. He started thinking about it seriously sometime in 1954. The standard Copenhagen interpretation, the one Bohr and Heisenberg had developed, said you couldn't ask what was happening before the measurement. The wave function was just a tool for calculating probabilities. It wasn't describing a real physical thing. Measurement was fundamental. The collapse was fundamental. Stop asking questions and calculate. Everett thought this was a cop-out. Not wrong exactly, but incomplete. Physics is supposed to describe the world as it is, not as it appears to observers. The Schrödinger equation, the core equation of quantum mechanics, doesn't include any collapse. It describes the wave function evolving smoothly and deterministically over time. Collapse was added by hand, an extra postulate grafted onto the theory to explain why we only see one outcome when we make a measurement. What if, Everett thought, we just didn't add that postulate? What if we took the Schrödinger equation seriously and let it run without interruption? What would happen? He started working through the math. It wasn't easy. The problem was entanglement. When you measure a quantum system, you don't stand outside it like a disembodied observer. You're made of particles too. Your measuring device is made of particles. When your device interacts with the quantum system, the wave functions of both get tangled up together. They become entangled. And once they're entangled, you can't describe the system's state without also describing your state. Everett realized that if you treat the entire process, the quantum system, the measuring device and the observer, as a single unified quantum system, then the Schrödinger equation describes all of it. And what it describes is not a collapse, it's a branching. Here's how it works. Suppose you've got an electron in a superposition of spin up and spin down. Before you measure it, the electron's wave function includes both possibilities. Now you bring in a measuring device, a detector that will register spin up or spin down. The detector is also in a definite state. Let's call it ready. When the detector interacts with the electron, the two become entangled. The combined wave function now describes a superposition of two scenarios. In one part of the wave function, the electron is spin up and the detector registers spin up. In the other part, the electron is spin down and the detector registers spin down. The Copenhagen interpretation says that at this point, the wave function collapses. One outcome becomes real, the other vanishes. But Everett said, why? There's nothing in the math that forces a collapse. Both parts of the wave function are still there, still evolving according to the Schrödinger equation. Both outcomes happened. The electron is spin up, and the detector shows spin up in one branch of the wave function. The electron is spin down, and the detector shows spin down in another branch. Both branches are real. Now bring in the observer. You look at the detector. When you do, you become entangled too. Your wave function splits. In one branch, you see the detector showing spin up. In the other branch, you see the detector showing spin down. Both versions of you are real. Both are experiencing a definite outcome. But the two branches have decohered. They no longer interact with each other. The version of you in the spin-up branch has no access to the spin-down branch, and vice versa. From your perspective, you only see one outcome. But that's because you only exist in one branch. The other version of you exists in the other branch, and that version also sees only one outcome. No collapse, no special role for consciousness, no mystery about when or how measurement happens. The wave function just keeps evolving, and every time a quantum interaction occurs, the wave function branches. Reality splits into parallel streams, one for each possible outcome. All outcomes are real. All versions of you are real. You just can't perceive the other branches because decoherence has separated them into independent, non-interacting realities. This was Everett's insight. And he called it the relative state formulation of quantum mechanics because each branch represents a relative state, a state of the universe relative to a particular observer. Later, in the 1970s, another physicist named Bryce DeWitt would give it a catchier name, the many worlds interpretation. Everett wrote it all up in his PhD thesis in 1956. The thesis was titled The Theory of the Universal Wave Function, and it was long, detailed, and mathematically rigorous. He showed that the Schrödinger equation, applied universally without any collapse postulate, naturally leads to branching. He showed that the appearance of collapse from the perspective of an observer inside the system is an inevitable consequence of entanglement and decoherence. He solved the measurement problem by showing there was no measurement problem. There's just the universal wave function evolving according to the laws of quantum mechanics, with every possible outcome realized in some branch. It was brilliant. It was airtight. And when Wheeler showed it to the other physicists at Princeton, they hated it. Niels Bohr was still the godfather of quantum mechanics in the 1950s. He was old by then, in his 70s, but his authority was absolute. The Copenhagen interpretation was his interpretation, and he defended it fiercely. When Wheeler told Bohr about Everett's idea, Bohr dismissed it almost immediately. He thought it was unnecessary, overly complicated, and philosophically misguided. Quantum mechanics worked fine as it was. Why multiply realities when one reality explained all the experiments? Wheeler, to his credit, tried to defend Everett. He arranged a meeting in Copenhagen in 1957 where Everett could present his ideas to Bohr and his students. The meeting was a disaster. Bohr didn't understand what Everett was trying to say, or maybe he understood and just didn't care. He kept insisting that the Copenhagen interpretation was correct and that Everett was solving a problem that didn't exist. Everett tried to explain that he wasn't contradicting the predictions of quantum mechanics, just offering a different interpretation of what the math meant. Bohr wasn't interested. The meeting ended with nothing resolved, and Everett thoroughly demoralized. He went back to Princeton, rewrote his thesis to make it shorter and less confrontational, and published a condensed version in Reviews of Modern Physics in 1957. The paper was called Relative State Formulation of Quantum Mechanics. It was 37 pages long, dense with equations, and almost nobody read it. The few physicists who did read it didn't take it seriously. Most thought it was an interesting mathematical exercise, but not a real alternative to Copenhagen. Some thought it was just wrong. A few thought it was crazy. Everett graduated with his PhD in 1957. He was 26 years old. He'd just written one of the most important papers in the history of quantum mechanics, and he couldn't get a job in physics. This is the part of the story that's hard to reconcile. Everett didn't try very hard to stay in academia. He didn't apply to universities. He didn't fight for his theory. He didn't spend years writing follow-up papers defending his ideas or responding to critics. He just left. He took a job at the Pentagon's Weapons Systems Evaluation Group, a think tank that did operations research for the military. He worked on game theory, nuclear strategy, optimization problems. He was good at it. He made good money. He had security clearance for classified projects. And he never published another paper on quantum mechanics. Why? That's a question his family and colleagues argued about for years. Some said he was disillusioned by the reception of his thesis. He'd worked incredibly hard on it. He'd solved a problem that had been bothering physicists for decades, and the response was indifference at best and hostility at worst. Why keep banging your head against that wall? Others said he just wasn't interested in the academic grind. He didn't want to teach undergraduates. He didn't want to apply for grants. He didn't want to spend his life attending conferences and schmoozing with senior professors. The Pentagon paid better, asked more interesting questions, and didn't care whether he believed in parallel universes. His daughter, Liz Everett, later said that her father was proud of his work, but didn't see the point in defending it if no one wanted to listen. He'd written it down. The math was there for anyone who cared to check. If people wanted to ignore it, that was their problem. He had other things to do, so he did other things. He worked on nuclear deterrence strategies. He calculated optimal bombing patterns. He developed algorithms for resource allocation. He got married, had 2 kids, bought a house in Virginia. He smoked 3 packs of cigarettes a day, drank heavily, and got fat. By all accounts, he was emotionally distant from his family. His son later described him as a lump of furniture at the dinner table, present but not really there, and for 20 years his paper sat in the library, unread and forgotten. Then, in the early 1970s, something shifted. Bryce DeWitt, a physicist at the University of North Carolina, read Everett's paper and realized it was being underappreciated. DeWitt had been thinking about quantum mechanics and gravity, trying to figure out how to apply quantum theory to the universe as a whole, and he saw that Everett's approach was the only one that made sense at cosmological scales. You couldn't have an external observer collapsing the wave function of the entire universe. The universe includes all observers. If quantum mechanics applies universally, then Everett's interpretation was the only one that worked. DeWitt started writing about it. He gave it the name Many Worlds Interpretation because he thought the phrase would capture people's attention better than relative state formulation. He was right. The name caught on. Other physicists started paying attention. Everett's paper started getting cited. Graduate students started reading it. By the late 70s, the Many Worlds Interpretation had gone from an obscure footnote to a major contender in the foundations of quantum mechanics. Everett heard about the renewed interest, but by then he didn't care much. He was in his late 40s, entrenched in his defense work, disconnected from the physics community. He gave a few talks at conferences in the late 70s, mostly at DeWitt's urging. But he didn't have the energy or the interest to become the public face of his own theory. He'd moved on. In 1982, at the age of 51, Hugh Everett III died of a heart attack in his home in McLean, Virginia. He was overweight, his health destroyed by decades of smoking and drinking. His family was caught completely off guard. His daughter was 19, his son was 17. Neither of them had understood what their father had done in physics. He'd never talked about it at home. As far as they knew, he was just a Pentagon consultant who worked on boring math problems. At the funeral, physicists showed up, colleagues from the 1950s, people Liz and Mark Everett had never met. They told stories about Hugh's brilliance, about his groundbreaking thesis, about how he'd changed the way physicists thought about reality. Liz was stunned. She had no idea. Her father, the guy who sat silently at the dinner table and drank too much, had apparently rewritten the rules of the universe, and he'd never mentioned it. Years later, Mark Everett, who became a musician and frontman for the band Eels, made a documentary about his father. He tracked down physicists who'd known Hugh, read his papers, tried to understand what the Many Worlds Interpretation actually meant. And what he found was a man who'd been profoundly isolated, both professionally and personally. A man who'd had one of the most important ideas in physics and then spent the rest of his life doing something else because no one wanted to listen. By the time Mark made that documentary, the Many Worlds Interpretation had become mainstream. Not universally accepted, no interpretation of quantum mechanics is universally accepted, but taken seriously by a large and growing number of physicists. Sean Carroll, a cosmologist at Caltech, has called it the best interpretation we have. David Deutsch, a pioneer in quantum computing, says it's the only interpretation that makes sense. Surveys of physicists show that while Copenhagen is still the most commonly taught interpretation, Many Worlds is gaining ground, especially among younger researchers. The irony is almost unbearable. Everett proposed the theory in 1957 and was ignored. He died in 1982, still largely ignored. And by the 1990s, the theory had become one of the foundational ideas in modern physics. He missed his own vindication by a decade. So why did it take so long? Why did the physics community ignore the Many Worlds Interpretation for 20 years before finally recognizing its value? Part of it was timing. In the 1950s, quantum mechanics was seen as a solved problem. The math worked. The predictions matched experiments. Most physicists were focused on applying quantum mechanics to new areas, nuclear physics, condensed matter, particle physics, not on reinterpreting the foundations. Everett's paper was a solution to a problem most people didn't think needed solving. Part of it was Bohr's authority. Bohr's word carried enormous weight, and if Bohr said the Copenhagen interpretation was correct, most physicists weren't going to argue. Challenging the Copenhagen interpretation in the 50s was professional suicide. You'd be labeled a crank, shut out of conferences, unable to get funding. Everett's paper was polite, rigorous, and mathematically sound, but it was also heretical. And heresy doesn't get tenure. And part of it was the sheer weirdness of the idea. parallel universes, infinite branching realities. Every time a particle makes a quantum decision, the universe splits. It sounds like science fiction. It sounds insane. Even now, with decades of serious work showing that the math holds up, a lot of people hear many worlds and think it's too absurd to be true. In the 1950s, that reaction was universal, but Everett was right. And the reason he was right is that he took the math seriously. He didn't try to force quantum mechanics to match his intuitions about how reality should work. He just followed the equations wherever they led. And they led to infinite universes, all equally real, all branching and diverging with every quantum interaction. This is the framework that makes quantum immortality possible. If every outcome happens, if reality splits into branches for every possible result, then the branch where you survive always exists. And if your consciousness can only follow the branches where you're alive, then from your perspective, you never die. You keep threading through the one timeline, the one absurdly improbable sequence of events where you continue to exist. Everett never wrote about quantum immortality. That idea came later, developed by other physicists building on his framework. But it's a direct consequence of his work. If the many worlds interpretation is correct, if the universal wave function really does branch into parallel realities, then you are immortal in exactly the disturbing, uncomfortable way we described at the start of this video. And that brings us to the next question. How many branches are there? How many parallel universes exist? Everett's math says the wave function branches every time a quantum event occurs. But how often is that? How big is the multiverse? The answer is going to make your head hurt. Let's start with the number you probably came here expecting to hear. 10 to the 500th power. That's a 1 followed by 500 zeros. To give you some perspective on how absurdly large that number is, the total number of atoms in the observable universe is estimated at around 10 to the 80th power. That's already incomprehensibly huge. Every atom in every star, every planet, every grain of dust, every molecule of gas floating in the void between galaxies, all of it adds up to 10 to the 80th. 10 to the 500th is bigger than that by a factor so enormous that there aren't enough atoms in the universe to represent it. If you wrote 10 on every atom in existence, you wouldn't even come close to writing out the full number. 10 to the 500th parallel universes is not just big, it's bigger than big has any right to be. But here's the thing, that number, as staggering as it is, doesn't actually come from the many worlds interpretation. It comes from string theory. Specifically, from the string theory landscape, the mind-bending idea that the fundamental laws of physics aren't unique. String theory, which attempts to unify quantum mechanics and gravity by proposing that particles are tiny vibrating strings in 10-dimensional space, predicts that there are roughly 10 to the 500th different ways the extra dimensions could be curled up. Each configuration produces a different set of physical constants, different strengths for gravity, electromagnetism, the nuclear forces, different masses for electrons and quarks, different values for the cosmological constant. Each configuration is called a vacuum state, and each vacuum state corresponds to a different kind of universe, a universe where atoms don't form, a universe where stars burn out in seconds, a universe where chemistry never gets complicated enough for life. And somewhere in that landscape of 10 to the 500th possibilities, there's at least one configuration that looks like ours, maybe more than one, maybe a lot more than one. But the total number of distinct universes in the string theory multiverse tops out at around 10 to the 500th. That's a lot of universes, but it's not infinite, it's a finite number. Absurdly large, yes, but still countable in principle. You could, if you had infinite time and infinite patience, list them all: Universe 1, Universe 2, Universe 3, all the way up to Universe 10 to the 500th. It would take you longer than the current age of the universe raised to the power of the age of the universe, but technically you could do it. The many worlds interpretation is different. The number of branches in the many worlds interpretation is not 10 to the 500th. It's not finite. It's not even countable. It's infinite. And depending on how you count, it might be growing so fast that calling it infinite doesn't even do it justice. Here's why. Every quantum event causes a branch. Every single time a particle's wave function includes multiple possible outcomes, the universe splits into separate branches, one for each outcome, and quantum events are happening constantly, not once in a while, not occasionally, constantly, everywhere. In every atom, in every photon, in every subatomic interaction occurring anywhere in the universe. Let's try to put a number on it. Take a single atom, just one. Hydrogen, the simplest atom in existence. One proton, one electron. That electron is in a quantum superposition of energy states. It's not sitting in a single definite orbit around the nucleus. It's spread out in a cloud of probability, and every time it interacts with anything, a photon, another atom, the electromagnetic field, it makes a quantum transition, up to a higher energy level, down to a lower energy level, staying where it is. Each transition is a quantum event. Each event branches the wave function. How often does this happen? Quantum transitions in atoms occur on timescales of nanoseconds to picoseconds. That's billionths to trillionths of a second. Let's be conservative and say each atom undergoes one quantum event per nanosecond. That's 1 billion events per second per atom. Now scale it up. The human body contains roughly 7 times 10 to the 27th atoms. That's 7 followed by 27 zeros. If each of those atoms is undergoing a billion quantum events per second, that's 7 times 10 to the 36th quantum events per second happening inside your body alone. Every single second you exist, your body is branching the universe 7,000 trillion times, and that's just you. There are roughly 8 billion people on Earth. Add in all the other living things, all the non-living matter, all the air molecules, all the photons bouncing around, all the cosmic rays zipping through the atmosphere, and the number of quantum events happening on Earth per second climbs into the tens of thousands of trillions, maybe higher. Now expand that to the entire observable universe. Roughly 10 to the 80th atoms, all of them undergoing quantum interactions constantly. The wave function is branching at a rate that makes 10 to the 500th look quaint. In the time it takes you to read this sentence, the many worlds multiverse has split into more branches than there are atoms in the universe. By the time you finish this chapter, the number of branches will have grown by a factor so large that the human brain cannot process it. This is exponential growth on a scale that defies comprehension. 10 to the 500th is a big number. But the many worlds interpretation isn't giving you 10 to the 500th universes, it's giving you infinity. An infinity that doubles, triples, explodes outward with every passing instant. An infinity that was already infinite a nanosecond ago and is somehow even more infinite now. Some physicists try to put a finer point on it. They'll say the number of branches grows proportionally to 2 to the power of n, where n is the number of quantum events. If you have one quantum event with 2 possible outcomes, you get 2 branches, 2 events, 4 branches, 3 events, 8 branches. By the time you've hit 100 quantum events, you're at 2 to the 100th branches, which is already more than a nonillion. By the time you've hit 1,000 events, you're so far beyond any number with a name that the naming system breaks down. And remember, we're talking about thousands of trillions of trillions of trillions of quantum events per second. The number of branches isn't just growing exponentially, it's growing at a rate that makes exponential growth look like a leisurely stroll. Now here's the part that's going to twist your brain. All of those branches are real, not hypothetical, not potential, real. They exist right now, in the same space you're occupying, overlapping with this room, this chair, this screen you're staring at. You just can't see them because they've decohered. They've separated into independent, non-interacting streams of the wave function. You're in one branch. Another version of you is in another branch. And a trillion other versions of you are scattered across a trillion other branches, all of them experiencing slightly different outcomes of the quantum events that have been occurring inside your body and around you since the moment you were born. This is what Everett meant when he talked about the universal wave function. The wave function doesn't describe a single particle or a single atom. It describes everything, the entire universe, all at once, in all possible states. And as that wave function evolves according to the Schrödinger equation, it splits and splits and splits, creating a tree of branching realities that grows faster than anything else in physics. The number 10 to the 500th shows up in another context, by the way, and this one is a bit closer to the many worlds interpretation. In the mid-90s, a mathematician named Peter Shor developed an algorithm that could factor large numbers exponentially faster than any classical computer. Factoring is the process of breaking a number down into its prime components. For small numbers, it's easy. 15 equals 3 times 5. Done. But for large numbers, numbers with hundreds of digits, factoring becomes insanely difficult. The best classical algorithms take longer than the age of the universe to factor numbers with more than a few hundred digits. Shor's algorithm, running on a quantum computer, could do it in seconds. The trick is that the quantum computer doesn't just try one solution at a time. It tries all possible solutions simultaneously, in superposition, and then collapses to the correct answer. Or more accurately, from the many worlds perspective, it splits into branches for every possible solution, and the branch you observe is the one that happens to contain the correct answer. When physicists calculated how many parallel computations Shor's algorithm would require to factor a 250-digit number, they came up with a figure around 10 to the 500th. That's how many branches the quantum computer would split into during the calculation. 10 to the 500th parallel universes, all running the same computation, all processing different potential factors, all collapsing, or from Everett's view, all continuing to exist, with you observing the branch that got the right answer. David Deutsch, one of the pioneers of quantum computing and a strong advocate for the many worlds interpretation, has argued that this is direct evidence that the multiverse is real. Where else, he asks, is the computation happening? A quantum computer with a few hundred qubits doesn't have enough physical resources in our universe to perform 10 to the 500th operations. The only explanation, Deutsch says, is that the computation is distributed across 10 to the 500th parallel universes. The quantum computer is literally borrowing processing power from other branches of the multiverse. Not everyone agrees with this interpretation. Some physicists think Deutsch is overstating the case, that quantum computers can be explained without invoking parallel worlds. But the math is hard to argue with. If you take the many worlds interpretation seriously, if you accept that the wave function really does branch into separate realities, then Shor's algorithm is proof, that those realities exist and that they're doing real computational work. And if 10 to the 500th branches can exist just to factor a single number, imagine how many branches exist for everything else that's ever happened. Let's zoom out for a second and talk about what this actually means. Your reality, the one you're experiencing right now, is just one branch. One thread in an incomprehensibly vast web of parallel timelines. Every decision you've ever made, every coin flip you've ever called, every random event that's ever affected your life, all of those moments created branches. In some branches, you made different choices. In some branches, the coin landed the other way. In some branches, you died years ago. In others, you're wildly successful, happier, healthier, richer. In still others, you're worse off. The version of you reading this right now is not special. You're not the main character. You're not the original. There is no original. Every branch is equally real. Every version of you is equally you. The only reason this particular version feels like the real one is because it's the one you're aware of. You can't perceive the other branches because they've decohered. They've split off and stopped interacting with this timeline. But they're out there, trillions of them, more than trillions. So many that the word trillions is an insult to the scale. And it's not just you. Every person you've ever met exists in countless branches. Your parents, your friends, your co-workers, everyone. In some branches, they made different choices. In some branches, they never met you. In some branches, they died before you were born. The version of them you know is just one thread in their own vast web of parallel lives. The same goes for history. Every historical event, every war, every election, every invention, all of those moments involved quantum events that could have gone differently. In some branches, World War II ended differently. In some branches, the Roman Empire never fell. In some branches, humans never evolved. The history you know, the timeline you inhabit, is one path through an unimaginably large space of possibilities. Most of those possibilities are similar to yours, small differences, minor variations, but some branches are radically different. Universes where the laws of physics are the same, the starting conditions were the same, but the random outcomes of quantum events led to completely different outcomes. This is the scale we're talking about, not 10 to the 500th, infinite. And not just infinite in the sense of going on forever. Infinite in the sense of containing every possible variation of every possible outcome of every possible quantum event that has ever occurred or will ever occur anywhere in the universe. If you're feeling existentially uncomfortable right now, you're not alone. A lot of physicists feel the same way. The many worlds interpretation solves the measurement problem, yes. It explains why we only see one outcome, even though the wave function describes many. It removes the need for wave function collapse and the special role of observers. It makes quantum mechanics cleaner, more elegant, more consistent. But the cost is accepting that reality is not a single story. It's an infinite library of stories, all happening simultaneously, all equally real, with you trapped in one narrow thread, unable to see or interact with any of the others. Some people hear this and think it sounds liberating. Every choice you didn't make, you made in another branch. Every path you didn't take, you took somewhere else. You're living every possible life across the multiverse. But that's not comforting when you think about it, because you, the version of you that's aware of this moment, don't get to experience those other lives. You're stuck here, in this branch, with this history, these choices, this outcome. The other versions of you aren't you in any meaningful sense. They're separate consciousnesses, living separate lives, completely unaware of your existence. You don't get to share their successes or avoid their failures. You're alone in your branch, surrounded by an infinite multiverse you can never touch. And here's where it gets darker. If every possible outcome happens, then the worst possible outcomes happen too. In some branches, every terrible thing you can imagine has occurred. In some branches, you've suffered unimaginably. In some branches, everyone you love has died in horrible ways. In some branches, the world ended in nuclear fire. In some branches, humanity never made it out of the Stone Age. All of those branches are real. All of those horrors actually happened somewhere in the multiverse. The many worlds interpretation doesn't just give you infinite possibilities, it gives you infinite tragedies. The flip side is also true. In some branches, everything went right. In some branches, you're living the best possible version of your life. In some branches, humanity solved all its problems and built a utopia. But you don't get to experience those branches either. You're stuck with the branch you've got. And statistically, most branches are mediocre. Not the best, not the worst, just somewhere in the middle, which is probably where you are. The many worlds interpretation forces you to confront the fact that your life, your choices, your experiences, all of it is just one random sample from an infinite distribution. You're not special, you're not chosen. You're just one outcome among an infinity of outcomes, and the only reason this outcome matters to you is because it's the one you happen to be conscious in. Now, if all of this sounds like an abstract philosophical exercise, something that doesn't really affect your day-to-day life, you're half right. The branching of the multiverse happens at scales far too small and far too fast for you to notice. You're not going to wake up tomorrow and suddenly perceive all the parallel versions of yourself. You're not going to slip between branches or communicate with alternate timelines. The branches have decohered. They've separated into independent realities that no longer interact. From a practical standpoint, you can ignore the multiverse and go about your life as if only one timeline exists. But here's the thing. If the many worlds interpretation is correct, if every quantum event really does split the universe into branches, then one particular implication becomes unavoidable. An implication that's been quietly sitting in the background of everything we've talked about so far. An implication that Max Tegmark formalized in the late 90s and that has been haunting people ever since. If every possible outcome happens in some branch, and if your consciousness can only follow branches where you remain alive, then from your subjective perspective, you can never die. In the vast majority of branches you die, but in at least one branch, no matter how improbable, you survive. And because you can only experience the branches where you're still conscious, you will always find yourself in the timeline where you made it through. The universe splits 1 trillion times per second. In most of those branches, nothing dramatic happens. You keep breathing, your heart keeps beating, life goes on. But in some branches, something goes wrong. A blood clot forms, a neuron misfires, a cosmic ray triggers a mutation. In those branches, you die, but not in all of them. In at least one branch, the blood clot dissolves, the neuron fires correctly, the cosmic ray misses, and your consciousness, unable to experience the branches where you died, threads itself into the single improbable timeline where you survived. This is quantum immortality. And if the many worlds interpretation is right, it's not just a thought experiment, it's a prediction. A prediction that you, personally, will never experience your own death, that you will keep surviving against increasingly impossible odds, threading through narrower and narrower branches of probability, until you're the last one left in a timeline so statistically unlikely that everyone around you thinks you should have died years ago. The multiverse isn't just big. It's not just infinite. It's structured in a way that traps you in your own awareness, forever, unable to escape the only thing you've ever been able to experience, your own continued existence. And that's where we're going next. The multiverse isn't just big, it's not just infinite, it's structured in a way that traps you in your own awareness, forever, unable to escape the only thing you've ever been able to experience, your own continued existence. And now we need to talk about what that actually means. Because if the many worlds interpretation is correct, if every quantum event really does split the universe into branches where every possible outcome occurs, then something very strange happens when you approach a moment that could kill you. The universe doesn't let you die. Not from your perspective anyway. It can't. Because the only branches you can ever experience are the ones where you're still alive to experience them. This is quantum immortality, and it's not a metaphor. It's a logical consequence of taking the many worlds interpretation seriously. Let's connect the pieces. Everett showed that the wave function never collapses. Every time a quantum measurement occurs, the universe branches into separate realities, one for each possible outcome. All outcomes happen. All branches are real. You just can't perceive the other branches because they've decohered, separated into independent streams that no longer interact with this timeline. Now apply that logic to a life or death situation. Suppose you're in a car accident, a bad one, the kind where survival depends on 1,000 tiny variables: the angle of impact, the speed of the vehicles, whether your seatbelt locks at exactly the right moment, whether the airbag deploys, whether a piece of metal crushes your skull or misses by a centimeter. All of these variables are influenced, at some level, by quantum events: the exact position of atoms in the metal, the precise timing of chemical reactions in the airbag propellant, the random firing of neurons in your brain as you react. In most branches, you die. The angle is wrong. The metal hits. Your brain stops functioning. From an outside perspective, from the viewpoint of anyone watching, you're dead. They see your body. They call the ambulance. They mourn. You are gone. But here's the problem. You can't experience that branch, because in that branch, your consciousness has ended. Your subjective awareness, the thing that makes you you, has stopped. There's no one left to observe the outcome. Death, by definition, is the cessation of experience. And if you can't experience it, then from your first-person perspective, it didn't happen. Meanwhile, in at least one branch, probably a very improbable branch, everything went right. The angle was different by a fraction of a degree. The metal missed. Your brain kept functioning. The quantum events that determine whether your neurons fire or don't fire all happen to tip in the direction that kept you conscious. That branch is statistically unlikely. It might be 1 in a million, 1 in a billion, 1 in a trillion. But it exists. The many worlds interpretation guarantees it exists. And because it's the only branch where you're still aware, it's the only branch you experience. You wake up in the hospital, confused, in pain, surrounded by doctors telling you it's a miracle you survived. And from your perspective, from the only perspective that matters to you, you did survive. You always survive. Because the branches where you died are branches you can never inhabit. Your consciousness threads itself through the single improbable timeline where you made it through. This is the core of quantum immortality. It's not that you're invulnerable. It's not that you can't be injured or that bad things can't happen to you. It's that the final moment, the moment your consciousness ends, is an event you can never experience. Because experiencing requires consciousness, and if consciousness has ended, there's no you left to experience the ending. Max Tegmark formalized this idea in 1998 with a thought experiment he called quantum suicide. It's brutal, it's disturbing. And it's one of the clearest illustrations of why quantum immortality is so unsettling. Here's how it works. You build a device connected to a quantum random number generator. The device measures a quantum event, something simple like the spin of an electron. 50% chance it's spin up, 50% chance it's spin down. If it's spin up, the device does nothing. If it's spin down, the device kills you instantly. Gunshot to the head. No pain, no suffering, just instant death. You activate the device. The quantum event occurs. The universe branches. In one branch, the electron is spin up. The device does nothing. You're alive. In the other branch, the electron is spin down. The device fires. You're dead. From an outside perspective, you have a 50% chance of dying. Flip a coin. Heads you live, tails you die. Run the experiment 10 times, and the odds of surviving all 10 trials are about 1 in 1,000. Run it 20 times, and the odds drop to about 1 in 1,000,000. Run it 100 times, and you're looking at odds so low they might as well be 0. But from your perspective, from the inside, you hear a click every single time. The device measures spin up. Nothing happens. You're alive. You run the experiment again. Spin up. Alive. Again. Spin up. Alive. You keep running it. 10 times, 20 times, 100 times. Every single time, you survive. Because in every branch where the device fired, you died. And in every branch where you died, there's no you left to observe the outcome. The only branches you experience are the ones where the device didn't fire, where the quantum event happened to land on spin-up, where you survived. To anyone watching, you died almost immediately. After 10 trials, they saw the device fire. They saw your body. They buried you. You've been dead for years, but from your perspective, you're still running the experiment, still surviving, still hearing that click, because you can only exist in the branches where you're alive to hear it. This is what Tegmark meant by quantum suicide. It's not a suggestion. It's not something anyone should actually try. It's a thought experiment designed to show what the many worlds interpretation predicts. And what it predicts is that if you run this experiment, you will subjectively experience immortality, not because you're lucky, but because the structure of the multiverse filters your consciousness through the only channels where consciousness can continue. The math is airtight. If the many worlds interpretation is correct, if every outcome of a quantum measurement is realized in some branch, then there is always a branch where you survive, always, no matter how improbable. And because your consciousness can only follow branches where you remain conscious, you will always find yourself in that branch. From the outside, this looks insane. You're the one in a trillion outlier who survived 100 coin flips. The universe bent probability into a pretzel to keep you alive, but from the inside, it just looks like you got lucky, because you have no access to the branches where you died. You can't see the bodies. You can't attend your own funeral. All you know is that you're still here. And here's where it gets worse, because this isn't just about thought experiments with quantum suicide machines. This is about every moment of your life. Every single day, you face quantum events that could kill you. A blood clot forming in your brain, a cosmic ray triggering a cancerous mutation, a random chemical reaction in your cells going wrong. Most of these events are harmless, but some of them, in some branches, are fatal. In most branches, you die. The blood clot forms, the cancer spreads, the chemical reaction poisons you. Your consciousness ends, but not in all branches. In at least one branch, the blood clot doesn't form. The cosmic ray misses. The chemical reaction goes the other way. And that branch, that single improbable thread of survival, is the one you experience. You can't experience the branches where you died because you're not there to experience them. Your subjective timeline, the story of your life from your own first-person perspective, is a sequence of survival events. Every close call you've ever had, every time you got sick and recovered, every accident you walked away from, those weren't just luck. Those were the moments where the multiverse branched and your consciousness threaded itself into the single timeline where you made it through, and it never stops. You keep aging. Your body keeps breaking down. You get weaker, sicker, more fragile. From an outside perspective, you're dying slowly. Your organs are failing. Your cells are giving up. But from your perspective, each moment that should be your last isn't, because the moment you cease to be aware is a moment you can never experience. You always wake up. You always keep going. Your consciousness finds the branch, no matter how unlikely, where your brain is still firing, where some version of you is still processing information. This is why Tegmark called it quantum immortality. Not because you live forever in a traditional sense. Your body doesn't stop aging. You don't become invulnerable. You don't gain superpowers. You just keep existing from your own subjective viewpoint, forever. Trapped in the only timeline where you're still aware, threading through increasingly improbable scenarios where you somehow, against all odds, survive. Now let's talk about why consciousness must follow the surviving branch, because this is where a lot of people get stuck. They hear the quantum suicide experiment and they think, okay, but why does my consciousness have to go to the branch where I survived? Why can't it just end? The answer is simple and terrible. Consciousness doesn't go anywhere. It doesn't move between branches. It just is. You are aware in the branches where you exist. You are not aware in the branches where you don't exist. There's no transfer, no hopping between timelines, no magical continuity of self that jumps from one universe to another. You simply cannot experience a timeline where you're dead because a dead person doesn't experience anything. Think about it this way. Right now, you're aware of this moment. You're reading these words or hearing this voice. You're experiencing the present. That awareness is happening in this branch of the multiverse. In another branch, a version of you died 5 minutes ago. That version is not aware. It's not experiencing anything. It's gone. And because it's gone, there's no perspective from which it exists. You, the version of you that's aware right now, only exist in branches where you're still alive. It's not that you chose this branch. It's not that some cosmic force guided you here. It's just that the only place you can be aware is in a place where you're still alive to be aware. Death is the absence of awareness, and you cannot experience absence, by definition, because experiencing requires presence. This is the subjective versus objective view of death in the multiverse. From an objective viewpoint, death happens all the time. In trillions of branches, you die. Your body stops. Your brain shuts down. The world moves on without you. Anyone observing from the outside will see you die eventually. They'll watch you get old, get sick, and stop breathing. They'll bury you. They'll remember you. From their perspective, you are mortal. But from your subjective viewpoint, from the first person, death never arrives. Because the moment it would arrive is the moment you stop having a viewpoint. You experience every second leading up to that moment. You feel the pain, the fear, the confusion, but the actual moment of cessation, the instant your awareness ends, you never get there, because getting there requires being there, and being there requires consciousness, and consciousness is exactly what ends. So your subjective experience is a string of survival events. Every moment you're aware is a moment where you survived. And because you're always aware in the present, you always survived to reach the present. The branches where you died are real, they exist. Versions of you are dead in countless timelines, But none of those versions are you, not the you that's aware right now. The you that's aware right now only exists in the branch where you're still alive, and that branch is the only one you'll ever experience. This leads to what some people call the last man standing idea. The concept is simple. In a multiverse where every outcome happens, there are branches where you die young and branches where you live to 100, branches where you die at 101, branches where you die at 102. For every age, for every moment, there's a branch where you die and a branch where you don't. And your consciousness always finds itself in the branch where you didn't, because the branches where you did are branches you can't experience. So from your perspective, you keep going. You outlive your friends, you outlive your family, you outlive everyone you know, not because you're special, not because you're blessed, but because your awareness can only exist in timelines where you're alive. And as long as there's a branch where you're alive, no matter how improbable, your consciousness is there. You become the last man standing, the sole survivor of a game you didn't know you were playing. Everyone around you dies, the world ages, society changes, and you're still here. Not because the universe wants you here, but because the structure of the multiverse guarantees that there's always a branch where you survived, and you're in it, because you have to be, because if you weren't, you wouldn't be experiencing anything. This is the paradox. Quantum immortality doesn't promise you a good life. It doesn't promise you health or happiness. It just promises you continued awareness. You could be in constant pain. You could be trapped in a failing body. You could be alone, confused, wishing for an end that never comes. Because the end, the moment your consciousness stops, is the one moment you can never reach. Some people hear this and think it sounds like a horror story. And they're right, it is. Imagine being 90, your body is breaking down, your mind is fading, you're ready to go, but you don't. You wake up the next day, and the next, and the next. Every time you think it's over, you find yourself still here, still aware, still trapped in a body that should have given up years ago. From the outside, people call it a miracle. They say you're resilient. They marvel at how you keep surviving. But you know the truth. You're not resilient, you're just stuck. Stuck in the only timeline where your consciousness can exist. Threading through narrower and narrower branches of probability as the odds of survival get smaller and smaller. And it gets stranger. Because if quantum immortality is real, then you've already been doing this your entire life. Every close call, every illness you recovered from, every accident you walked away from, those were moments where you threaded into the survival branch. You think you've been lucky, but maybe you haven't. Maybe you've just been experiencing what the multiverse looks like from the inside when you're subjectively immortal. You'll never know. That's the trap. You can't tell the difference between a universe where you're just lucky and a universe where quantum immortality is real. Because from your perspective, they look identical. You survive either way. The only difference is the explanation. In one universe, you got lucky. In the other, you are always going to survive because the structure of reality guarantees it. And here's the final twist. If quantum immortality is real, you're not the only one experiencing it. Everyone is. Every conscious being in the universe is threading through their own survival branches. From their perspective, they never die. They keep going, outliving everyone around them, trapped in their own subjective timeline. So the world you're living in right now might be populated entirely by quantum immortals. People who think they've been lucky, who think they've survived by chance, but who are actually trapped in the same structure you are. You'll never meet them, not in the way you'd recognize. Because their survival branches and your survival branches don't have to overlap. In your branch, your friend died 5 years ago. In their branch, you died 5 years ago. Both of you are subjectively immortal, threading through your own improbable timelines, unaware that the other is doing the same thing in a parallel reality. This is what the many worlds interpretation predicts. This is what the math says. If every outcome happens, if the wave function never collapses, if consciousness can only exist in branches where it remains conscious, then from a first-person perspective, death is impossible, not in the sense that you can't be killed, but in the sense that you can never experience being killed. The moment your awareness would end is a moment that, by definition, you can never inhabit. And that raises a question nobody has a good answer to. What is consciousness? If your subjective experience always threads into the survival branch, if your awareness is somehow tied to the structure of the multiverse in a way that keeps you locked into timelines where you continue to exist, then what is consciousness actually doing? Is it a passive observer riding along on quantum events? Or is it something more fundamental, something built into the fabric of reality itself? That's where we're going next. Because if quantum immortality is real, if your awareness really does persist across every possible timeline where you survive, then consciousness isn't just an emergent property of a brain, it's something deeper, something stranger, something that might be woven into the quantum mechanics of the universe itself. And that raises a question nobody has a good answer to. What is consciousness? If your subjective experience always threads into the survival branch, if your awareness is somehow tied to the structure of the multiverse in a way that keeps you locked into timelines where you continue to exist, then what is consciousness actually doing? Is it a passive observer riding along on quantum events? Or is it something more fundamental, something built into the fabric of reality itself? Because here's the uncomfortable part. If quantum immortality is real, if your awareness really does persist across every possible timeline where you survive, then consciousness cannot just be what most neuroscientists say it is. It cannot just be neurons firing in patterns. It cannot just be an emergent property of a sufficiently complex brain, the way wetness is an emergent property of water molecules, or the way traffic jams emerge from individual cars following simple rules. If quantum immortality works, if your subjective experience is genuinely locked into survival branches by the mechanics of the multiverse itself, then consciousness has to be doing something. It has to be playing a role in the structure of reality that goes deeper than anything we've acknowledged. This is not a comfortable conclusion. Most scientists, most of the time, prefer explanations that keep consciousness in its place. A byproduct of biology, a trick of evolution, a useful illusion generated by 3 pounds of meat inside your skull. The brain is a machine, the argument goes, an extraordinarily complicated machine, but a machine nonetheless. Feed it inputs, sensory data from the world, and it generates outputs, thoughts, decisions, the sensation of being someone. Consciousness is what it feels like to be a brain processing information, nothing more. Certainly nothing that requires rewriting the laws of physics. But quantum immortality, if it's real, doesn't care what makes scientists comfortable. It demands an explanation for why your awareness threads through survival branches. Why your subjective experience, out of all the possible experiences across all the branches of the multiverse, always finds itself in timelines where you remain conscious. And the standard neuroscience answer, that consciousness is just neurons firing, doesn't cut it, because neurons fire in all the branches. In the branches where you die, your neurons were firing right up until they stopped. So why does your awareness only track the branches where the firing continues? The question forces you to confront something most people spend their entire lives avoiding. What is consciousness actually? Not what does it do, Not where does it come from in an evolutionary sense, but what is it? At the most fundamental level, what is the thing that makes you aware? Philosophers call this the hard problem of consciousness. The phrase was coined by David Chalmers in the mid-1990s, and it's one of those ideas that sounds simple until you really think about it. The easy problems of consciousness, Chalmers said, are things like figuring out how the brain processes sensory information, how it integrates data from different sources, how it controls behavior. Those are hard problems in a practical sense, sure, but they're the kind of problems science knows how to approach. You study the brain, you map the circuits, you figure out which neurons do what. Difficult but doable. The hard problem is different. The hard problem is explaining why any of that processing feels like something, why there's a subjective experience attached to it, why it's like something to be you. You can map every neuron in the brain. You can trace every signal, every chemical cascade, every electrical pulse, and at the end of all that mapping, you still haven't explained why the lights are on, why there's an inner experience, why there's a you inside your head watching the show. This is the gap that neuroscience hasn't closed. We can explain in increasing detail how the brain works. We can explain how visual information gets processed, how memory gets stored, how decisions get made. But we cannot explain why any of that is accompanied by the feeling of being someone, why there's a first-person perspective, why the universe, from your vantage point, has a center. And quantum immortality makes the hard problem harder. Because if your awareness is threading through survival branches, if the structure of the multiverse is somehow filtering your subjective experience into timelines where you remain conscious, then consciousness isn't just an emergent property of a brain. It's a feature of reality that interacts with quantum mechanics. It's something that the multiverse is tracking, something that matters to the way the wave function evolves. That should not be true. At least, not according to the way most physicists think about quantum mechanics. The standard view, even in the many worlds interpretation, is that consciousness is irrelevant. The wave function branches whether or not anyone is watching. Decoherence happens automatically, driven by interactions with the environment. Observers are just physical systems like any other. Your brain is made of particles. Those particles obey quantum mechanics. When your brain becomes entangled with a quantum system, it branches just like everything else. Consciousness, in this view, is along for the ride. It doesn't do anything. It's just the subjective sensation of being a particular branch of the wave function. But that explanation struggles when you apply it to quantum immortality. If consciousness is just along for the ride, why does it always end up in the survival branch? The wave function branches into timelines where you die and timelines where you don't. Both are real. Both versions of your brain exist, one still firing, one not. Why does your awareness track the firing brain and not the silent one? What is it about consciousness that makes it selectively follow the branches where the brain keeps working? The obvious answer is that a non-firing brain can't support consciousness. Dead brains don't think, fine. But that just rephrases the question. Why is your awareness tied to the functioning of this particular brain in this particular branch? Why doesn't it track a different brain in a different branch? Why does it feel continuous, like a single stream of experience, when the multiverse is branching trillions of times per second? This is where some physicists start to get uncomfortable, and where a few start to wonder if consciousness might be more fundamental than we've been assuming. Not an emergent property, not a byproduct, but a basic feature of the universe, like space or time or energy. Something that doesn't arise from the complexity of brains, but is woven into the fabric of reality itself. One of the people who took this idea seriously was Max Planck. Yes, that Max Planck, the guy who started the whole quantum revolution in 1900 when he proposed that energy comes in discrete chunks. Planck spent the later years of his life thinking about consciousness, and in 1931 he wrote something that still gets quoted by people trying to bridge the gap between physics and the mind. He said, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. Everything that we talk about, everything that we regard as existing, postulates consciousness." Planck wasn't being mystical. He was making a point about the structure of knowledge. Every measurement, every observation, every piece of data we have about the universe comes filtered through consciousness. We never access raw reality. We access our experience of reality, and that experience, that consciousness, is the one thing we can't reduce to something else. Because any attempt to explain consciousness presupposes consciousness. You need to be aware to understand the explanation. This is the bind. Consciousness is the tool we use to investigate the world. It's also the thing we're trying to investigate, and we can't step outside it to get an objective view. We're stuck inside the thing we're trying to explain. Some physicists have argued that this bind is telling us something important, that consciousness isn't just an observer of reality, but a participant. That quantum mechanics, with its emphasis on measurement and observation, is forcing us to confront the fact that the observer cannot be cleanly separated from the observed. The most famous version of this idea came from Eugene Wigner, one of the pioneers of quantum mechanics and a Nobel Prize winner. Wigner proposed what's now called the Wigner's friend thought experiment, a variation on Schrödinger's cat designed to show that consciousness might play a direct role in collapsing the wave function. The argument goes like this. Suppose your friend is in a lab measuring the spin of an electron. The electron is in a superposition of spin up and spin down. Your friend measures it, and from your friend's perspective, the wave function collapses. The electron is now definitely spin up or definitely spin down. Your friend knows the result, but you're outside the lab, you haven't looked. From your perspective, the entire lab, including your friend, is in a superposition. Your friend measured spin up in one branch and spin down in another. The wave function hasn't collapsed for you yet. It only collapses when you open the door and ask your friend what they saw. So when did the collapse actually happen? When your friend measured the electron, or when you became aware of the result? Wigner suggested that the collapse happens when a conscious observer becomes aware of the outcome, not when a measurement device registers a result, not when a photon interacts with a detector, but when a mind perceives it. This idea was controversial when Wigner proposed it, and it's still controversial now. Most physicists reject it. They argue that consciousness is not special, that measurement is just a physical interaction, and that bringing consciousness into the picture adds unnecessary complications. Wigner himself eventually backed away from the idea, though he never completely abandoned it. But the idea keeps coming back. Because if you take the many worlds interpretation seriously, if you accept that all branches are real and that the wave function never collapses, then you still have to explain why you experience only one branch, why your awareness follows one thread through the multiverse. And the only thing that's unique about your thread is that it's the one you're conscious in. Which brings us to a hypothesis that's even more controversial. The idea that consciousness itself is a quantum phenomenon. That the thing happening inside your brain when you're aware is not just neurons firing in classical patterns, but a quantum process, something that operates at a deeper level than the biology we can see. The most developed version of this idea is called Orchestrated Objective Reduction, or ORC-OR for short. It was proposed in the mid-1990s by Roger Penrose, a mathematical physicist at Oxford, and Stuart Hameroff, an anesthesiologist and consciousness researcher at the University of Arizona. Penrose and Hameroff argue that consciousness arises from quantum processes occurring inside structures called microtubules, tiny protein scaffolds inside neurons. Here's the basic idea. Neurons are complicated. They're not just wires that fire electrical signals. Inside each neuron is a complex internal structure, a kind of skeleton made of microtubules. These microtubules are involved in all sorts of cellular processes, including the transport of molecules and the structural integrity of the cell. Penrose and Hameroff propose that they're also doing something else. They're hosting quantum computations. According to R, the microtubules inside neurons can sustain quantum superpositions, states where particles are in multiple configurations at once. These superpositions involve electrons or other particles in the protein structures of the microtubules. The superpositions are orchestrated, meaning they're organized and controlled by biological processes inside the cell. And they undergo objective reduction, meaning they collapse not because of observation, but because of a process related to gravity. This is where Penrose's contribution comes in. Penrose has argued for years that consciousness involves something non-computable, something that can't be replicated by a classical computer. He thinks that the collapse of the wave function is not random, as standard quantum mechanics suggests, but is influenced by the structure of space-time itself. Gravity, Penrose says, plays a role in determining when and how quantum superpositions collapse. And when those collapses happen inside the microtubules of neurons, they generate moments of conscious awareness. It's a bold idea. If it's true, then consciousness is not just an emergent property of neurons firing. It's a quantum process. Your awareness, the thing that makes you you, is happening at the level of quantum events inside the protein structures of your brain cells. And those quantum events are sensitive to the fabric of space-time, to the curvature of gravity, to the deep structure of the universe itself. Most neuroscientists are skeptical. They point out that the brain is a warm, wet, noisy environment. Quantum superpositions are fragile. They decohere almost instantly when they interact with their surroundings. How could quantum states survive long enough inside a neuron to do anything meaningful? Hameroff and Penrose have responses to this. They argue that the microtubules are shielded, that the structure of the proteins creates a kind of protected environment where quantum coherence can last long enough to matter. But the debate is far from settled. There's no direct experimental evidence that quantum processes in microtubules are linked to consciousness. The hypothesis remains speculative. But here's why it matters in the context of quantum immortality. If consciousness is a quantum process, if your awareness is tied to quantum events in your brain, then your consciousness is part of the wave function. It's part of the thing that branches. And that opens the door to a different way of thinking about why your awareness threads through survival branches. Because if consciousness is quantum, then it's not just observing the branching, it's participating in it. It's entangled with the rest of the universe at a fundamental level. And entanglement, as we know from quantum mechanics, is non-local. It connects systems across space in ways that defy classical intuition. If your consciousness is quantum, if it's entangled with the broader wave function of the universe, then it's not confined to the inside of your skull. It's part of a larger structure, a network of quantum correlations that spans the multiverse. And in that structure, your awareness might naturally thread through the branches where it can continue to exist. Not because of some mystical force guiding you, but because the quantum correlations that make up your consciousness only persist in branches where the physical substrate, your brain, remains functional. This is speculative. Let's be very clear about that. Or is not a proven theory. Quantum theories of consciousness in general are not proven. They're hypotheses, ideas that some researchers think are worth exploring, and that most researchers think are either wrong or unfalsifiable. But they're taken seriously by a non-zero number of physicists and neuroscientists, precisely because they offer a potential bridge between the hard problem of consciousness and the weird features of quantum mechanics. And there's another angle. If consciousness is fundamental, if it's not an emergent property but a basic feature of the universe, then you start to edge into territory that sounds a lot like panpsychism. Panpsychism is the idea that consciousness, or at least some proto-form of consciousness, is a universal property, that it's not just humans and animals that have it, that it's everywhere, in some form, at every level of reality. Electrons don't think, obviously, but maybe they have some rudimentary form of experience, some tiny spark of interiority that aggregates into larger forms of consciousness when systems get complex enough. This sounds crazy to most people, and it's definitely outside the mainstream of science. But it has a respectable philosophical pedigree, and in the last couple of decades, it's gotten a second look from philosophers and even a few physicists. The appeal is that it dissolves the hard problem. If consciousness is fundamental, then you don't have to explain how it arises from non-conscious matter. It was there all along. The brain doesn't create consciousness. It organizes it, channels it, amplifies it into the complex form we recognize as human awareness. If panpsychism is true, then quantum immortality takes on a different flavor. Your consciousness isn't something that starts when your brain forms and ends when your brain stops. It's part of the fabric of reality. It's always been there, and it will always be there, threading through the branches of the multiverse in whatever form can sustain it. Your human awareness, the thing you recognize as yourself, is just one temporary configuration of a more fundamental consciousness that pervades everything. Again, this is speculation piled on speculation, but it's speculation that some serious people are taking seriously. And it's speculation that quantum immortality forces you to confront. Because if your awareness genuinely persists across every survival branch, if you are subjectively immortal, then consciousness is not what we've been taught to think it is. It's not a fragile emergent property that winks out when your neurons stop firing. It's something more durable, something that the structure of the multiverse tracks and preserves, and that brings us back to the observer problem in quantum mechanics. One of the oldest and strangest features of quantum theory is that observation matters. The act of measuring a quantum system affects the outcome. Before measurement, the system is in a superposition. After measurement, it's in a definite state. And nobody has ever been able to explain exactly what counts as a measurement or why measurement should have this effect. The many worlds interpretation sidesteps the problem by saying there is no collapse. The superposition continues. All outcomes happen, but that doesn't fully answer the question. Because from your perspective, from the inside, you experience one outcome. The superposition, from your viewpoint, has effectively collapsed. Why? What makes your perspective special? The uncomfortable answer is that your perspective is the only one you have access to. You are the observer. You are the thing doing the experiencing. And if consciousness is quantum, if it's entangled with the wave function in some fundamental way, then the observer isn't external to the system. The observer is part of the system. Your awareness is woven into the fabric of reality, and the branching of the multiverse is something you participate in, not something you watch from the outside. This doesn't mean you control the branching. You don't get to choose which outcome happens. All outcomes happen, but your consciousness, your subjective thread of awareness, is part of the wave function that's branching. And that thread, by its nature, only exists in branches where you remain conscious. It cannot exist anywhere else, because consciousness requires a functioning substrate, and in the branches where your brain stops, there is no substrate. So the observer problem and the hard problem of consciousness might be two sides of the same coin. Both are asking the same question in different ways. What is the relationship between the thing that observes and the thing that's observed? In classical physics, the question doesn't come up. The observer is just another physical system, and observation is just another interaction. But in quantum mechanics, the observer cannot be cleanly separated from the observed, and in the many worlds interpretation, the observer becomes part of the branching structure itself. If that's true, then consciousness is not a passenger in the universe. It's a participant. It's built into the way reality works at the most fundamental level, and quantum immortality, far from being a strange side effect of the math, is a direct consequence of that participation. Your awareness threads through survival branches because that's the only place your awareness can be. The structure of reality, the quantum mechanics of the multiverse, ensures it, not as a kindness, not as a gift, but as a feature of the system, which raises one final deeply unsettling question. If consciousness is fundamental, if it's quantum, if it's non-local and entangled with the structure of the multiverse, then what happens to it when your brain finally does stop functioning in every branch? Because eventually, no matter how improbable the survival thread gets, your body will break down. The human lifespan, even in the most unlikely branches, has limits. Cells can only divide so many times, proteins denature, entropy wins. At some point, there are no more survival branches. The thread runs out, so does your consciousness end. Or does it continue in some other form, no longer tied to this particular brain, no longer recognizable as you, but still part of the quantum fabric of reality? Does it dissolve back into the universal wave function, the same fundamental consciousness that might underlie everything? Nobody knows. The math doesn't tell us, the philosophy doesn't tell us, and the experiments that might answer the question are impossible to run. Because the only way to know what happens to consciousness after death is to die. And if quantum immortality is real, you never get there. You keep surviving, threading through narrower and narrower branches, unable to experience the one thing that might answer the deepest question of all. This is what quantum immortality implies about consciousness, that it's not local, that it's not confined to your brain, that it's entangled with the structure of reality itself, that it participates in the branching of the multiverse in ways we don't fully understand, that it might be fundamental, woven into the fabric of existence, persisting in forms we can't yet imagine. And if that's true, then the next question becomes unavoidable. What does it mean to live in a universe where you never die? Not just in a mathematical sense, not just as an abstract consequence of the many worlds interpretation, but in a lived, experienced, day-to-day sense. What does it do to your psychology? What does it do to your ethics? How do you live a meaningful life when you know, or at least suspect, that from your perspective there is no end? That's the question we need to answer next. Because quantum immortality isn't just a physics problem or a consciousness problem, it's a human problem. And the implications, psychological and ethical, are going to be harder to face than anything we've talked about so far. Let's start with the simplest question. What does it do to you to believe this? Not to accept it as an abstract possibility, not to entertain it as a thought experiment over coffee, but to actually believe deep in your bones that you are subjectively immortal. That no matter what happens, no matter how dangerous the situation, no matter how bad your health gets, you will always wake up. You will always find yourself in the branch where you survived. What does that belief do to a person? The first thing it does is strip away one of the fundamental guardrails that keeps human behavior in check: fear of death. We don't usually think of fear as a good thing, but the fear of death is what stops most people from doing genuinely stupid things most of the time. You don't walk into traffic because you might get hit. You don't jump off buildings because you might die. You wear your seatbelt. You avoid poison. You look both ways before crossing the street, all because somewhere in the back of your mind is the knowledge that your body is fragile and your life can end. That fear is calibrated by experience. You see other people die. You see accidents. You hear about diseases. You internalize the message that death is real, that it can happen to you, that it will happen to you eventually, and that knowledge shapes your behavior. It makes you cautious. It makes you value your life because you know it's finite. Now imagine you believe in quantum immortality. Really believe it, not as a fun idea to kick around at parties, but as a fact about how reality works. You know that from your subjective perspective, you cannot die. Every time you face a potentially fatal situation, the universe will split into branches where you die and branches where you don't. And your consciousness, unable to experience the branches where you died, will always find itself in the survival branch. You are guaranteed to survive, always. From your point of view, you are unkillable. What happens to your behavior? The obvious answer is that you start taking risks. Why wouldn't you? If you know you're going to survive, why not try things that would normally be suicidal? Why not drive recklessly, play with fire, experiment with dangerous drugs? From your perspective, the worst-case scenario doesn't exist. You'll always wake up. You'll always find yourself in the timeline where you made it through. Except it's not that simple. Because while you are guaranteed to survive from your perspective, everyone else is not. Your friends are not subjectively immortal from your point of view. They are mortal. They can die. They will die. And your reckless behavior can kill them. Let's say you believe in quantum immortality and you decide to drive drunk. You get in your car. You speed down the highway. You swerve between lanes. In most branches, you crash. In most of those branches, you die. But in at least one branch, you don't. The angle was slightly different. The car missed the barrier by inches. You walked away. And because you can only experience the branch where you survived, that's the branch you're in. From your perspective, you got lucky. You're fine. But your passenger isn't fine. Your passenger, who does not share your quantum immortality, who does not get to thread through survival branches from their own independent perspective that happens to overlap with yours, died in that crash. In your branch, their body is in the wreckage. And you're standing outside the car, confused, because from your point of view, you survived. You always survive. But they didn't. This is the first ethical problem with quantum immortality. If you believe it applies to you, you cannot assume it applies to anyone else. You are locked in your own subjective timeline. Everyone else is locked in theirs, and those timelines do not have to overlap in convenient ways. Your survival branch might be their death branch. Your quantum immortality does not protect them. It only protects you. So believing in quantum immortality doesn't just make you reckless with your own life. It makes you dangerous to everyone around you, because you lose the ability to take their mortality seriously. From your perspective, you're invincible, but they're not. And your behavior, shaped by the belief that you'll always survive, can kill them in ways you'll never fully experience because you're not in the branches where you see the consequences. This creates a kind of solipsistic nightmare. If you truly believe in quantum immortality, you have to accept that everyone else in your timeline is, in some sense, a supporting character in your survival story. They're real, yes. They're conscious, yes. But their timelines and your timeline are not the same. You are threading through the branches where you survive. They are threading through their own branches, and the overlap is temporary. Eventually, your survival branch and their survival branch will diverge. They'll die from your perspective, and you'll die from theirs. And neither of you will know that the other is continuing on in some other timeline, threading through their own improbable sequence of survival events. This is what it means to live in a multiverse, where everyone is subjectively immortal from their own perspective, but not from anyone else's. You are surrounded by people who will die. You will watch them die. You will bury them. You will mourn them. And all the while, you will keep surviving. Not because you're special, but because your awareness can only exist in branches where you're alive. And those branches, by definition, are branches where everyone else eventually stops showing up. The psychological impact of this belief is hard to overstate. Most people derive meaning from their relationships, from the sense that they're connected to other people, that they matter to someone, that their life is woven into a larger social fabric. But if you believe in quantum immortality, that fabric unravels, because everyone you know is temporary. They're only in your timeline for as long as your survival branch and their survival branch happen to overlap, and that overlap will end. It always ends. From your perspective, you will outlive everyone. You become the last man standing, not because you chose to, not because you're stronger or smarter or luckier, but because the structure of the multiverse guarantees that there's always a branch where you survive, and you're in it, and everyone else eventually is not. This leads to what some researchers have called a consciousness trap. The term was used by a few theorists writing about the psychological implications of quantum immortality in the late 2010s. The idea is that your awareness is locked into the most improbable timelines, the ones where you keep surviving against increasingly impossible odds. And as those odds get longer, as your survival becomes more and more unlikely, the timeline you're in becomes stranger. Because here's the thing, if you're threading through the single branch where you survive a car crash, you're already in an improbable timeline. Most branches, you died, but you're in the rare one where you didn't. Now imagine that happens again, and again, and again. Every time you face a potentially fatal event, you thread into the survival branch. And each time, the branch you're in becomes a little more improbable, a little more unlikely, a little more detached from the median experience of reality. After enough iterations, you're living in a timeline that is so statistically unlikely, so absurdly improbable, that it barely resembles the world anyone else is experiencing. You are the person who survived 100 coin flips, the person who walked away from 1,000 car crashes, the person who recovered from every disease, every injury, every moment that should have killed them. From the outside, your life looks like a miracle. From the inside, it just feels like existence, because it's the only existence you've ever been able to experience. But the timeline you're in is not stable, it's not predictable. Because you're threading through the narrowest possible path of survival, reality around you starts to behave strangely. Not because the laws of physics are breaking down, but because you're living in the tail end of the probability distribution, the place where weird things happen because they're the only things that can happen if you're going to survive. Some theorists have speculated that if quantum immortality is real, people experiencing it would notice increasing cognitive dissonance, memories that don't quite line up, events that seem to have happened differently than you remember, a sense that the world is not behaving the way it used to. Not because your memory is failing, but because you're threading through timelines that are increasingly divergent from the median. Your survival branch and the branches where most people live are splitting further and further apart. and the version of reality you're experiencing is no longer the version most people would recognize. This is the fragmentation, the disintegration of self. Your memories are composites of slightly different timelines. The version of you that survived the car crash at 20 has memories from a branch that diverged from the branch you're in now. The version of you that survived the illness at 30 has memories from yet another branch. Over time, your sense of continuity, your sense of being a single person with a single history starts to break down. Because you're not a single person with a single history. You're a thread of awareness that has passed through dozens, hundreds, thousands of divergent timelines, picking up memories and experiences from branches that no longer connect cleanly to the branch you're in now. You start to feel like a patchwork, a composite of different versions of yourself, stitched together by the accident of survival. And the more you survive, the more fragmented you become. Because each survival event is a branch point, and each branch point is a place where your history could have gone differently. In most branches, it did. You're just in the one where it didn't. This is not eternal life in any meaningful sense. This is eternal disintegration. A slow unraveling of your sense of self, stretched across an infinite number of increasingly improbable timelines, unable to die, unable to stop, unable to escape the only thing you've ever been able to experience, your own continued awareness. Now let's talk about the ethical implications of suffering. Because if quantum immortality is real, it doesn't just mean you can't die. It means you can't die even when you want to, even when continued existence is unbearable. Some researchers have classified quantum immortality as an S risk. That's short for suffering risk, a term used in existential risk studies to describe scenarios where sentient beings experience extreme and prolonged suffering. Most discussions of existential risk focus on extinction, the end of humanity, the destruction of all conscious life. Those are X risks, existential risks, scenarios where everything ends. S risks are different. S risks are scenarios where things don't end, where conscious beings are trapped in states of prolonged suffering with no escape. Quantum immortality is an S risk because it traps you in existence regardless of whether that existence is desirable. You cannot choose to stop. You cannot opt out. Your consciousness threads through survival branches whether you want it to or not. And some of those branches, maybe most of them after a certain point, involve suffering. Imagine you're 100 years old, your body is failing, you're in constant pain. Every organ is breaking down, every joint aches, your mind is slipping, you're ready to die. You want to die, but you don't. Because, from your perspective, every moment that should be your last isn't. You wake up the next day, and the next, and the next. The universe keeps threading you into the single improbable branch where your brain is still firing, where some version of you is still aware, even though your body is a wreck and your mind is barely holding together. This is not immortality in the sense of eternal youth. This is immortality in the sense of eternal decay. You are trapped in a body that should have given up years ago. And the longer you survive, the worse it gets. Because the only branches where you can still be conscious are branches where your brain is still functioning. But your brain is part of your body, and your body is falling apart. So the version of you that's still aware is a version that's living in a body that's barely working, in pain, confused, wishing for an end that never comes. From an outside perspective, this looks like a medical miracle. The doctors marvel at how you keep surviving. Your family calls it resilience. But from your perspective, it's torture. You are locked in the consciousness trap, unable to die because your awareness can only exist in branches where you're still aware. And those branches, no matter how improbable, always exist. The ethical question becomes, is this a fate worse than death? Most people, when they imagine immortality, picture something pleasant. Eternal life with health and vitality, the chance to see the future, to experience new things, to keep learning and growing. But quantum immortality doesn't promise you that. It promises you continued awareness. That's all. It doesn't care whether you're happy. It doesn't care whether you're in pain. It just keeps you conscious. And here's the disturbing part. If quantum immortality is real, then it applies to everyone. Every conscious being. Every person who has ever lived or ever will live is, from their own perspective, subjectively immortal. Which means every person who is suffering, who is in pain, who is trapped in unbearable circumstances, is also trapped in the consciousness trap. They cannot die, they cannot escape. They can only thread through the single improbable branch where they remain aware. And if that branch involves prolonged suffering, they're stuck with it. This has implications for how we think about end-of-life care, about euthanasia, about the ethics of prolonging life in cases of terminal illness. If quantum immortality is real, then turning off life support doesn't end suffering from the patient's perspective. It just threads them into a different branch. A branch where the life support stayed on, or a branch where they recovered against all odds, or a branch where something else happened that kept them conscious. They don't get to die. They just get to experience a different version of survival. This makes the question of suffering much harder. Because in a universe where no one can truly die from their own perspective, suffering becomes the only variable that matters. You can't escape existence, but you can exist in states of greater or lesser suffering. And the ethics of how we treat people, how we alleviate pain, how we provide comfort, become even more urgent. Because if quantum immortality is real, every moment of suffering is a moment that someone is trapped in, unable to escape, unable to die, just enduring. Now let's address the question that's probably been bothering you since the start of this video. Is the version of you that survives really you? Or is it just a version of you? This is where quantum immortality brushes up against the oldest problem in philosophy. The problem of personal identity. What makes you you? Is it your body, your memories, your personality, your continuity of consciousness? And if the multiverse is constantly branching, if every quantum event creates a new version of you in a new timeline, then which version is the real you? The standard answer from the many worlds interpretation is that there is no real you. All versions are equally real. Every branch contains a version of you that's just as much you as any other version. The version of you reading this right now is not more real than the version of you in a parallel branch who decided to stop reading 5 minutes ago. Both are you. Both are conscious. Both have their own subjective experience, but that answer doesn't feel satisfying. Because from your perspective, from the first person, you only experience one timeline. You only have one stream of consciousness. You can't access the other branches. You can't communicate with the other versions of yourself. So from your point of view, you are singular. You are one person, living one life, making one set of choices. The other versions might exist, but they're not you in any meaningful sense, because you're not aware of them. Quantum immortality sharpens this problem, because if your consciousness always threads through survival branches, if you always find yourself in the timeline where you didn't die, then the version of you that's aware right now is the version that survived. But in how many branches did you die? In how many timelines does a version of you no longer exist? Thousands? Millions? Trillions? You are the one who made it through. But are you the same person who started this journey, or are you a composite? A thread of awareness that has passed through so many branch points, so many divergences, that your identity is no longer cleanly connected to the person you were when you were born? Think about it this way. Every time you face a quantum branch point, a moment where you could die or survive, the version of you that survives is slightly different from the version that would have died. Not in any obvious way, not in a way you'd notice, but different. Your memories include the survival event. Your personality is shaped by having lived through it. You are changed by the experience. And over time, over thousands of survival events, those small changes add up. The version of you that's aware right now is not the same as the version that would have existed if you'd never faced those branch points. This raises a disturbing possibility that the version of you experiencing quantum immortality is not the original you. Not because there's some metaphysical essence that defines the original, but because your identity has been reshaped over and over by the process of threading through survival branches. You are not the person you would have been if you'd died at 20. You're the person who survived past 20, and that person, shaped by survival, is different. Some philosophers have argued that this means quantum immortality is not really immortality at all. It's a kind of death by degrees, a slow replacement of who you were with who you've become. Each survival event is a small death, a pruning away of the versions of you that didn't make it, and the version that remains is a survivor, yes, but not the same person who started. You've been changed by the process of surviving. And after enough changes, are you still you? There's no clear answer to this. Personal identity is slippery. Most people feel like they're the same person they were 10 years ago, even though almost every cell in their body has been replaced, even though their memories have shifted, even though their personality has changed. Continuity of consciousness gives us the feeling of being a single, continuous self, even though the evidence suggests we're more like a river, always flowing, always changing. Never quite the same from one moment to the next. Quantum immortality just makes that process more explicit. You are a thread of awareness passing through countless branches, shaped by countless survival events, never quite the same as you were a moment ago. And the longer you survive, the more pronounced the changes become. You are not immortal in the sense of being unchanging. You are immortal in the sense of continuing to change forever, unable to stop, unable to die, unable to become anything other than the next version of yourself in the next survival branch. And here's the final psychological twist. If you believe in quantum immortality, you have to accept that you've already died, thousands of times, in countless branches. The version of you that's aware right now is not the only version. It's just the version that survived long enough to be aware of this moment. But there are other versions that died yesterday, last week, 10 years ago, versions that never made it past childhood, versions that died in accidents you don't even remember facing because you only remember the branches where you survived. From an outside perspective, you have died thousands of times. Your family has mourned you in countless timelines. Your friends have attended your funeral in branches where the car crash went differently, where the illness took hold, where the random quantum event tipped the wrong way. Those deaths are real. Those branches exist. You are not immortal from an objective standpoint. You're only immortal from your own subjective standpoint, because you can't experience the branches where you died. This is what it means to live in a multiverse. You are simultaneously alive and dead, depending on which branch you're looking at. And the version of you that's aware right now, the version reading these words, is just one thread in an incomprehensibly vast web of timelines. Most of those threads ended. You're in the one that didn't. And that thread will keep going, not because you're special, but because it's the only thread you can ever be aware of. So what does this do to the meaning of life? If you're subjectively immortal, If you know that from your perspective you'll never die, does life still have value? Do your choices still matter? Or does everything become meaningless because there's no end point, no final reckoning, no moment where the story ends and you get to look back and evaluate what it all meant? Most people derive meaning from finitude, from the knowledge that time is limited, that each moment is precious because there are only so many moments. If you have infinite time, if you know you're never going to run out of chances, then why does any particular moment matter? Why strive? Why grow? Why care? But that framing misses something important. Quantum immortality doesn't give you infinite time in the sense of having all the time in the world to do whatever you want. It gives you continued awareness in the narrowest possible survival thread. You don't get to choose which branch you're in. You don't get to live a comfortable eternal life. You get to exist in the one timeline where you didn't die, and that timeline, statistically, is getting weirder, more fragmented, more improbable with every moment you survive. So the meaning of life, if quantum immortality is real, doesn't come from finitude. It comes from the fact that your experience, your subjective awareness, is the only thing you have. You are trapped in it. You can't escape it. You can't stop it. The only thing that matters is how you choose to experience it, what you pay attention to, how you treat the people around you, knowing that they're temporary, that they'll die from your perspective even though they're subjectively immortal from theirs. How you find moments of beauty, of connection, of meaning in a timeline that's increasingly absurd and improbable. You are living in the survival branch, the one where you made it through. And the question is not whether that branch will end. The question is what you do with it. How you live in the knowledge that every moment is improbable, that you shouldn't be here. That statistically, in most branches, you're already dead. And yet here you are, still aware, still experiencing, still capable of making choices, even if those choices are shaped by the narrowing path of survival you're on. This is not comforting. Quantum immortality is not a gift. It's a condition, a feature of the multiverse that you're stuck with, whether you want it or not. And the psychological and ethical implications are as unsettling as the physics. You are immortal. You are alone. You are fragmenting. You are trapped. And the only way out is a way you can never reach. Because the moment you would reach it, the moment your consciousness would end, is the moment you stop being able to experience anything at all. So you keep going, threading through survival branches, outliving everyone, fragmenting into a patchwork of memories from divergent timelines, trapped in the consciousness trap, unable to die, unable to stop, unable to escape the only thing you've ever been able to know, that you exist, that you are aware, that you are here. And now we come to the question that's been lurking underneath everything we've talked about. The question that the physics can't answer, that the philosophy can't settle, that the experiments can't test. The question that matters more than any other. Is it true? Is quantum immortality real? Or is it just a thought experiment that got out of hand? A mathematical curiosity that doesn't apply to the actual world we live in. Because if it's not true, then everything we've just discussed is fiction. An elaborate intellectual exercise with no bearing on reality. But if it is true, then everything changes. Your life, your death, your choices, your understanding of what it means to be conscious, all of it is different than you thought. So which is it? How do we know? And what does the evidence actually say? That's the question we're going to answer next. And the answer is going to be more unsettling than either yes or no. And now we come to the question that's been lurking underneath everything we've talked about. The question that the physics can't answer, that the philosophy can't settle, that the experiments can't test. The question that matters more than any other. Is it true? Is quantum immortality real? Or is it just a thought experiment that got out of hand? A mathematical curiosity that doesn't apply to the actual world we live in? Because if it's not true, then everything we've just discussed is fiction, an elaborate intellectual exercise with no bearing on reality. But if it is true, then everything changes. Your life, your death, your choices, your understanding of what it means to be conscious, all of it is different than you thought. So which is it? How do we know? And what does the evidence actually say? That's the question we're going to answer next. And the answer is going to be more unsettling than either yes or no. Let's start with what we actually know, not what we speculate, not what the math suggests might be true. What we know, what we can measure, what we can test. We know quantum mechanics works. That's not in dispute. Every prediction quantum mechanics makes about the behavior of particles has been confirmed by experiment, sometimes to absurd levels of precision. The electron's magnetic moment, for example, has been measured and calculated to agree within 1 part in a trillion. Quantum mechanics predicts the energy levels of atoms, the behavior of semiconductors, the operation of lasers, the structure of molecules. It is the most successful scientific theory ever devised in terms of predictive accuracy. If quantum mechanics were wrong, your phone wouldn't work, your computer wouldn't work. Half the technology you use every day would stop functioning. So quantum mechanics is real. The math is real. The predictions are real. What's not settled is what the math means. What is actually happening when a quantum system is in superposition? What is actually happening when a measurement occurs? Is the wave function a real physical thing or just a tool for calculating probabilities? Do particles have definite properties before we measure them, or do those properties only come into existence when we look? These are questions about interpretation, and here's the uncomfortable truth. Physics doesn't have a way to settle questions about interpretation, because interpretations, by definition, make the same predictions. They give you the same experimental outcomes. They just tell different stories about what's happening underneath. The many worlds interpretation is one of those stories. It says the wave function is real, it never collapses, and every time a quantum measurement occurs, the universe branches into parallel realities where all possible outcomes happen. It's a clean story. It's mathematically elegant. It solves the measurement problem by dissolving it. No collapse, no special role for observers, no boundary between quantum and classical. Just the Schrödinger equation, running without interruption, producing a tree of branching realities. And because the many worlds interpretation is logically consistent with the math of quantum mechanics, because it makes all the same predictions as every other interpretation, you can't prove it wrong by experiment. There's no test you can run that would distinguish between a universe where the wave function collapses and a universe where it branches. Both interpretations predict the same outcomes for every measurement you could ever make. This is deeply frustrating if you're trying to figure out what's actually true, because science is supposed to work by testing hypotheses. You propose an idea, you design an experiment, you see if the results match the prediction. If they do, the idea gains support. If they don't, the idea is wrong. That's how we've built up our understanding of the world. Test, refine, test again. But interpretations of quantum mechanics don't work that way. They're all compatible with the same experimental results, so you can't test them against each other. You can only evaluate them on other grounds: mathematical simplicity, conceptual elegance, philosophical coherence, how well they fit with your intuitions about how reality should work. And on those grounds, physicists are split. Some think the many worlds interpretation is the most natural reading of the math. It takes the Schrödinger equation seriously. It doesn't add extra postulates like wave function collapse. It doesn't require a special role for observers. It's clean. Others think it's absurd. They point out that it multiplies entities beyond necessity. You start with one universe and end up with an infinity of universes, all to avoid admitting that the wave function collapses. That's a lot of metaphysical baggage to carry just to keep the math simple. And the idea that all these parallel universes are real, that they exist right now, overlapping with this room, even though we can never see them or interact with them, strikes a lot of people as untestable speculation rather than science. The Copenhagen interpretation, the one Bohr and Heisenberg developed in the 1920s, is still the most commonly taught interpretation in physics courses. It says the wave function is just a tool for calculating probabilities. When you measure a quantum system, the wave function collapses and you get a definite outcome. Don't ask what's happening before the measurement. Don't ask why the collapse happens. Just calculate the probabilities and move on. Shut up and calculate. This interpretation has the virtue of not requiring parallel universes. You don't have to believe in branching realities or infinite versions of yourself. The world you see is the world that exists. One timeline, one history, one reality, clean and simple, but it has problems too. The biggest one is the measurement problem. When does the collapse happen? What counts as a measurement? Is it when a photon hits a detector? Is it when the detector sends a signal to a computer? Is it when a human looks at the computer screen? The Copenhagen interpretation doesn't give a clear answer. It draws a fuzzy line between the quantum world, where superposition is real, and the classical world, where things have definite properties. But it never says where that line is or why it exists. Some physicists prefer hidden variable theories. These are interpretations that say quantum mechanics is incomplete. Particles do have definite properties all along. We just can't measure them all at once. There's a deeper layer of reality underneath the probabilities, a set of hidden variables that determine the outcomes. If we could see those variables, the randomness of quantum mechanics would disappear and everything would be deterministic again. The most well-known hidden variable theory is called Bohmian mechanics, after physicist David Bohm. It adds an extra layer to quantum mechanics, a pilot wave that guides particles along definite trajectories. The wave function is real in Bohmian mechanics, but it doesn't collapse and it doesn't branch. It just guides particles through space. Every particle has a definite position and momentum at all times. We just can't measure both at once because our measurements disturb the system. Bohmian mechanics makes the same predictions as standard quantum mechanics for every experiment, so you can't prove it wrong, but it's more complicated. It adds extra structure, extra assumptions, extra variables. And most physicists think that if two theories make the same predictions, you should prefer the simpler one. So Bohmian mechanics hasn't caught on, even though it's logically consistent and solves some of the conceptual problems people have with quantum mechanics. So where does that leave us? With multiple interpretations, all consistent with the math, all making the same experimental predictions and no clear way to choose between them. Physicists have been arguing about this for nearly a century, and they're no closer to consensus now than they were in the 1920s. Surveys of physicists show that opinions are all over the place. One survey conducted at a Quantum Foundations conference in 2011 found that 42% of respondents favored the Copenhagen interpretation, 18% favored many worlds, and the rest were split between various other interpretations or had no preference. A more recent survey in 2019 found that many worlds had gained ground, especially among younger physicists, but it's still not the majority view. The point is, there is no consensus. The smartest people in the field, the ones who work with quantum mechanics every day, cannot agree on what it means. And if they can't agree, how are the rest of us supposed to figure it out? Now let's talk specifically about quantum immortality. Because even if you accept the many worlds interpretation, even if you believe the wave function really does branch into parallel realities, quantum immortality is still a step further. It's an implication of many worlds, but it's not something the interpretation requires you to believe. It's a consequence you get if you follow the logic in a particular direction. And that logic has holes. The first hole is timing. Quantum immortality assumes that your consciousness threads through the survival branch at the moment of a life or death event. But when does that moment occur? When does the branching happen? If you're in a car crash, the universe doesn't split at the moment your body stops functioning. It splits at the moment the quantum event that determined the crash occurred. Maybe it was a random fluctuation in the firing of neurons in your brain a second before the crash. Maybe it was the precise position of atoms in the metal of the car when it was manufactured. The point is, the branching happens upstream at the quantum level, long before the macroscopic outcome becomes clear. So by the time you're in the crash, by the time your body is being crushed, the branching has already happened. You're already in a specific branch. And in most branches, you die. There's no mechanism for your consciousness to jump from a branch where you're dying to a branch where you survive. Because the branches have already separated, they've decohered, they no longer interact. This is a serious problem for quantum immortality. The theory requires that your consciousness somehow knows which branch leads to survival and threads itself into that branch. But consciousness is a product of your brain, and your brain is a physical system that's already in a specific branch. It can't jump between branches after the fact. The branching happens at the level of quantum events, not at the level of conscious experience. By the time you're aware of what's happening, you're already locked into a branch. And if that branch is one where you die, there's no escape hatch. Some defenders of quantum immortality argue that the branching is continuous, that every moment involves countless quantum events, and that your consciousness is constantly threading through survival branches. So even if you're in a branch where you're dying, there are still quantum events occurring in your brain, and those events are still branching, and at least one of those branches leads to survival. But this runs into the problem of biology. Your brain is not infinitely flexible. If your skull is crushed, if your brain tissue is destroyed, there's no quantum branch where that damage didn't happen. The damage is macroscopic. It's not a quantum superposition. It's a definite, irreversible physical event. And once that event has occurred, there's no branch where your brain is still functioning normally. The branching can't undo macroscopic damage that's already been done. So quantum immortality, even if the many worlds interpretation is correct, doesn't work the way the thought experiment suggests. You can't survive events that cause immediate, irreversible destruction of your brain. Because the branches where you survive are branches where that destruction didn't happen. And those branches separated from your branch long before you became aware of the danger. The second hole is aging. Even if quantum immortality could keep you alive through accidents and injuries, it can't stop your body from aging. Aging is not a quantum process. It's a result of accumulated damage to cells, the shortening of telomeres, the buildup of waste products, the gradual failure of organs. These are macroscopic, deterministic processes. There's no quantum branch where you don't age. So even if you thread through survival branches for every accident, every illness, every moment that could kill you, you're still getting older. Your body is still breaking down. And eventually, your body will reach a point where it can no longer support consciousness. Your brain will degrade. Your neurons will stop firing. And when that happens, there's no survival branch left, because consciousness requires a functioning brain, and a brain that's degraded past a certain point can't function. Some people have argued that quantum immortality would thread you into increasingly improbable branches where aging slows down, where your body repairs itself in unlikely ways, where you live to 150 or 200. But that's not how biology works. The laws of thermodynamics don't allow for bodies to spontaneously repair themselves without energy input. And the energy input required to keep a human body functioning indefinitely is enormous. There's no quantum branch where entropy reverses, where your cells stop accumulating damage, where you become immortal in the traditional sense. So quantum immortality, even if it were real, is not true immortality. It's a temporary extension, a threading through survival branches that eventually runs out when your body reaches the end of its biological lifespan. And that lifespan, no matter how improbable the survival branches you thread through, has an upper limit. The third hole is the unfalsifiability problem. Quantum immortality cannot be tested. There is no experiment you can run that would prove or disprove it, because the only way to test it would be to put yourself in a life or death situation and see if you survive. But if you survive, you can't tell whether it was quantum immortality or just ordinary luck. And if you die, you're not around to report the results. Max Tegmark's quantum suicide thought experiment was designed to illustrate this. You run the experiment, you pull the trigger 100 times, and from your perspective, you hear a click every time. But that doesn't prove quantum immortality. It could just mean you got incredibly lucky. 1 in a trillion odds, sure, but not impossible. From an outside perspective, you're dead. You died on the first or second pull, but you can't see that perspective. You only have your own subjective experience. And your subjective experience is consistent with both quantum immortality and extraordinary luck. This is why quantum immortality is not a scientific hypothesis. It's a philosophical speculation. Science requires testable predictions, theories that can be proven wrong by experiment. Quantum immortality makes no testable predictions. It predicts that from your subjective perspective, you will always survive. But that's a prediction you can never verify, because you can't compare your subjective experience to an objective baseline. You can't see the branches where you died. You can't measure the probability distribution. You're stuck inside your own perspective, and from that perspective, survival is the only outcome you can ever experience. So quantum immortality is unfalsifiable, and unfalsifiable claims are not science. They're philosophy. They're interesting to think about, sure, but they don't belong in the same category as testable scientific theories. There's been pushback on quantum immortality from physicists who specialize in quantum foundations. A paper published in 2009 by a researcher identified as VVS explicitly debunked the quantum suicide argument. The paper argued that the many worlds interpretation does not imply certain survival. The branching happens according to the probabilities given by the wave function. If there's a 50% chance you survive a quantum suicide event, then in half the branches you survive, and in half you die. The version of you that survives experiences survival. The version that dies experiences nothing. But the probabilities don't change just because you can only experience the survival branch. You still die in half the branches. Quantum immortality doesn't make you immortal. It just makes it so you can't experience the branches where you died. This might sound like a semantic distinction, but it's important. Quantum immortality suggests that your consciousness is guaranteed to survive, that the universe will bend probability to keep you alive. But that's not what the math says. The math says that all outcomes happen according to their probabilities. In most branches, you die. In a few branches, you survive. Your subjective experience is biased toward survival because you can only be aware in the branches where you survived. But that doesn't mean survival is guaranteed. It just means your experience is filtered. Some critics go further and argue that consciousness doesn't thread through branches at all, that each branch contains a separate version of you with its own consciousness. The version of you in the survival branch is not the same consciousness as the version in the death branch. They're both you, but they're separate, independent streams of awareness. There's no continuity between them, no thread connecting them. Each version experiences its own branch and nothing else. If that's true, then quantum immortality is even less meaningful. Because the version of you that survives is not the you that was in danger. It's a different you in a different branch. The you that was in danger is dead in most branches. The survival branch contains a copy of you, yes, but it's not a continuation of your consciousness. It's a parallel consciousness that happens to share your memories up to the branch point. This raises deep questions about personal identity that we touched on earlier. If every branch contains a separate version of you, then which one is the real you? The answer is all of them and none of them. You are not a single entity. You are a collection of parallel consciousnesses, each experiencing its own timeline, each unaware of the others. And the idea that one of those consciousnesses is immortal is meaningless because there's no privileged consciousness, no central you that persists across branches. So where does all this leave us? With a theory that's unfalsifiable, a logic that has holes, and a set of assumptions about consciousness and identity that are far from settled. Quantum immortality is not a scientific fact. It's a speculative implication of a speculative interpretation of quantum mechanics. It's interesting, it's thought-provoking. It forces you to confront uncomfortable questions about consciousness, identity, and the nature of reality. But it's not something you can know is true. And here's the thing. Even if it is true, even if the many worlds interpretation is correct, and your consciousness really does thread through survival branches, the implications are not what most people imagine. You are not invincible. You are not immortal in any meaningful sense. You are a subjective observer, locked into a single thread of experience, unable to access the other branches, unable to verify that they exist, unable to escape the narrow channel of awareness that defines your existence. And that channel ends. Maybe not today, maybe not in 50 years, but it ends. Because consciousness requires a functioning brain, and brains do not last forever. So the grand question, is quantum immortality true, doesn't have a satisfying answer. The honest answer is we don't know. We can't know. Not with the tools we have. Not with the understanding we have. The math allows for it. The logic suggests it. But the evidence is absent. And without evidence, all we have is speculation. But here's the more important question. Does it matter? Does believing in quantum immortality change how you should live? For most people, the answer is no. If quantum immortality is real, you're already experiencing it, and you don't need to do anything differently. You can't escape it. You can't control which branch you're in. You just keep living, making choices, experiencing moments, the same way you would if quantum immortality were false. The structure of your subjective experience doesn't change based on whether the multiverse is real. You still experience one timeline, one stream of events, one set of choices and consequences. Knowing that there might be parallel versions of you in other timelines doesn't change the fact that you only have access to this one. And if quantum immortality is false, if the many worlds interpretation is wrong, if consciousness ends when your brain stops, then nothing changes either. You still live your life the same way. You still make choices, build relationships, pursue goals. The fact that your life might have an endpoint doesn't rob it of meaning. If anything, it gives it urgency. The knowledge that time is limited makes each moment more valuable. So, whether quantum immortality is true or false, the practical implications for how you should live are the same. Be kind to the people around you because they're real and they matter, regardless of whether they're temporary in your timeline or subjectively immortal in their own. Make choices that align with your values because those are the only choices you have control over. Experience the world fully because this moment, this timeline, this thread of awareness is the only one you can ever inhabit. The rest is speculation. And maybe that's the real lesson of quantum immortality. Not that you're immortal, not that reality is split into infinite branches, but that your subjective experience is all you have. You are locked inside your own consciousness, unable to step outside it, unable to verify what lies beyond it. You can theorize about parallel universes, about branching realities, about versions of yourself living different lives in different timelines, but you can never see them, you can never touch them, you can never know for certain that they exist. What you do know, the only thing you can know with absolute certainty, is that you are aware right now, that you exist in this moment, that you are experiencing this timeline, this reality, this narrow channel of consciousness that defines your existence. And that's enough. That has to be enough, because it's all you've got. Quantum immortality is a mirror. It reflects back the deepest questions about what it means to be conscious, what it means to exist, what it means to know anything at all. And the answers it gives, or rather the answers it refuses to give, are unsettling. You cannot prove you're immortal. You cannot prove you're not. You cannot prove the multiverse exists. You cannot prove it doesn't. You are stuck in your own perspective, navigating a reality you can only experience from the inside, with no way to step back and see the bigger picture. And maybe that's the point. Maybe the universe isn't designed to give you answers. Maybe it's designed to give you questions. Questions that force you to confront the limits of what you can know, the boundaries of what you can experience, the strange and uncomfortable truth that your consciousness is both the most certain thing you know and the thing you understand the least. So is quantum immortality true? The answer is, it doesn't matter. Not in the way you think it does. What matters is how you live with uncertainty. How you make meaning in a universe that refuses to tell you what's real. How you treat the people around you, knowing they're temporary from your perspective, even if they're immortal from theirs. How you experience each moment, knowing it's the only moment you can ever truly inhabit. You are here. You are aware. You exist. And whether that existence continues in parallel branches, whether your consciousness threads through survival timelines, whether you're immortal or mortal or something in between, the only thing that matters is this moment, right now, the one you're experiencing. The one that's happening while you listen to these words, while you sit in this chair, while you exist in this timeline. That's all you have. That's all you've ever had. And that, whether you're immortal or not, is the only truth that really matters. So here we are, at the end of a story that might not have an ending. You've followed the logic this far. You've seen where the math leads. You've stared into the structure of a universe that splits every time a particle makes a choice, a reality where every possible outcome happens somewhere, where your consciousness threads through the single improbable channel where you remain aware. You've confronted the idea that from your perspective, from the only perspective you'll ever have, death might not be something you can reach. And now you're sitting with that, trying to decide what it means, trying to figure out if it changes anything. Here's what I can tell you. You will never know if quantum immortality is real. Not with certainty, not in this lifetime or any other. The evidence will never arrive because the structure of the theory makes evidence impossible. You are locked inside your own subjective experience, and that experience is consistent with both a universe where you're immortal and a universe where you just keep getting lucky until you don't. The data set you have access to, your continued existence, proves nothing. It's just the baseline, the only thing you can ever observe. But maybe that's not the question that matters. Maybe the question isn't whether you're immortal. Maybe it's what you do with the awareness you have right now, this moment, this thread, this narrow, improbable timeline where you happen to be conscious. You didn't choose to be here. You can't choose to leave. You're just here, aware, experiencing, making choices that ripple forward into a future you'll never fully understand. And whether that future branches into infinite parallel realities or collapses into a single inevitable end, you still only get one perspective, yours, the one happening right now, the one that's always been happening, the one that will keep happening until it doesn't, or until it does, forever, in ways you'll never be able to see from the outside. You are the observer trapped inside the experiment, and the experiment is your life. That's the only thing quantum mechanics has ever really told us. Not that reality is strange, but that you are strange. That consciousness, your consciousness, is the most certain and most mysterious thing in the universe. You cannot escape it. You cannot explain it. You can only experience it. So experience it, not because you're immortal, not because you're mortal, but because right now, in this moment, you are. And that moment is the only one that's ever been real.